This is an aptitude based question. A sentence has been given which is an interrogative sentence. From where are they bringing their books? And in response to that question we have a sentence dash bringing dash books from dash. So we need to fill appropriate pronouns in these three blanks such that the question will make sense and it will be grammatically correct. Now we shall see that dash bringing. So here we should fill a pronoun referring to a person such as who is bringing the books. So the most appropriate choice will be they are. They are bringing dash books. Now here we can fill a pronoun which may be appropriate to the person or to the book, which means they are bringing their books. So there will be the appropriate choice for this particular blank, which says that they are bringing their own books from some place. So here we should fill a pronoun which would refer to some place, and from the given options there is the appropriate choice for this. So the complete sentence will be they are bringing their books from there. Now this there is referring to the person, the group of people who is bringing those books, and this there is referring to the place from where those books are being brought. So the appropriate choice will be they are, there and there, which will be option B. This is an aptitude based question. We have to fill this blank with the appropriate word. A dash investigation can sometimes yield new facts, but typically organized ones are more successful, which means there is a comparison being made between this particular kind of investigation and the organized type of investigation. It is saying that this investigation can sometimes yield new facts, but the typically organized ones are often more successful. So in this particular blank we need to fill some word which is in opposite sense, such as organized. So the choices can be something which is disorganized or in a undirected way, which is uncontrolled or unorganized. That kind of investigation can sometimes give us new facts, but in comparison to that the typical organized investigations are more successful. So from the given options we need to identify the words which are similar in meaning to disorganized or undirected, and we can find out that meandering is one such word. A meandering investigation means a kind of investigation which is very much disorganized and undirected, so that is very few times successful in yielding new facts in comparison to the organized one. The other three options are not in the similar sense as meandering, so we eliminate those and we go with just this particular option A, which is meandering. This is a simple geometry based question. There is a square of area D, which means its sides will be of length root D and root D, all the sides, because the area of a square is the side square. So if its area is D, then the length of its sides has to be root D. We need to identify the area of a circle which has the diagonal of this square as its diameter. The diagonal of this square, the length of this diagonal will be found out using the Pythagoras theorem. We know that. Let us call this length to be L. Then L square will be the sum of squares of these two, which will be D plus D or 2D. So if L square equal to 2D, then this length L will be root 2 times of D. Hence the length of hypotenuse we have got is root 2D, and now this length will be the diameter of a circle. So its radius will be half of this root 2D upon 2, or we can call it root of D by 2. Hence the area of this circle, which is given as pi r squared, will be pi times this root D by 2 in the whole square, and that gives us pi D by 2. So the area of this particular circle having diagonal of this square as its diameter will be pi D by 2, which is the option D. So that is our answer. This is an aptitude based question. We need to determine the missing number which can fit in this given sequence. As we can see here, the consecutive numbers 2 and 12 have a relation of 6 times between them, which means 2 multiplied 6 times will give us 12. Then 12 multiplied 5 times will give us 60. Then 60 into 4 will give 240. So we have forming a decreasing product series over here. Here we have a product 3 times, then 2 times, So over here we will have a one-time product, which means 1440 one times will give us 1440 again, and then that at the end 0 times will give us 0. So yes, 1440 is satisfying this given sequence, and that would be the correct option to fit in this particular blank. So the right option is B. This question is based upon mathematical logic. We want to find the smallest natural number which, when divided either by 20 or by 42 or by 76, will leave the same remainder 7 in every case. So let us take these numbers 20, 42 and 76 and express them as a product of prime factors. So this 20 can be written as 2 square into 5, 42 will be written as 6 into 7, which means 2 into 3 into 7. The 76 will be 19 into 4, which is 2 square into 19. Now let us find LCM of all of these. For LCM, we take the product of common factors into non-common factors. So here's the common factor among all of them is it 2. So we eliminate that 2 from each of them. Then this will become 2 into 5. This will be 3 into 7 and this will be 2 into 19. So now we take the product of all these factors. So 2 square into 3, 5, 7 and 19. This actually gives us 7980. That is the LCM of these three numbers. So the smallest number which will be divisible by each of them and will leave the remainder 7 will be this 7980 plus 7, which will be 7987, which is option C in our case. Or we can also verify using another method, which will be, let us look at option A. It is 3047. So let us just subtract 7 from that. It will give 3040. Now we can check if it is divisible by all of them, and we will find that it is not divisible by 42. Hence this option will be eliminated. Same for the option B. Subtracting 7 from it gives 6040, which is not divisible by 42, but it is divisible by the other two. So this option will also be eliminated. Now looking at option C and D, these both will be found to be divisible by all the three numbers, but we want the smallest natural number. So this option 63840, it is divisible by all of them, but since we wanted to choose the smallest one, we shall go for option C, which is 7987. So that is the correct option. This is a mathematical aptitude question. We have the terms P, Q and R such that the product PQR is non-zero, and we have three equations such that P raised to minus 6 equal to 1 by Q, Q raised to minus Y equal to 1 by R, and R raised to minus Z equal to 1 by P. Now using these three, we need to determine the value of the product X, Y, Z. As we can see, these terms X, Y and Z appear only in the power of these three equations. So we will need to make use of logarithmic and exponential functions to get the result. Let us reframe these three equations as, first one can be written as Q equal to 1 by P raised to minus X, or we can write that as Q equal to P raised to X. Similarly, this becomes R equal to Q raised to Y, and this becomes P equal to R raised to Z. Now let us multiply these three equations, then we shall get PQR equal to P raised to X, Q raised to Y, R raised to Z. Now again this shall give us, after cancelling PQR from both the sides, we shall get P raised to X minus 1, Q raised to Y minus 1, R raised to Z minus 1 equal to 1. Now the only values of X, Y and Z that will satisfy this equation will be 1 each. We will need to have X equal to 1, Y equal to 1 and Z equal to 1. Since the product PQR is non-zero, which means all of them are non-zero individually. Hence, if all of them are non-zero and the product of their powers is 1, then all of them need to have a 0 power. So that gives us the value of X, Y and Z all to be 1. Hence their product X, Y, Z will also be 1, and that will be our result. Option C. This question is based upon simple geometry. We need to find the sum of these two angles DEC and BFC based on the given figure. Let us number these angles as the following: 1, 2, 3, 4, 5 and 6. What we actually want to find is the sum of angles DEC and DFC. So they will be, we have DEC over here, which is angle 4, plus angle BFC, which means angle 5. So now let us look at the triangle DEC, this particular triangle, and let us apply external angle property upon this. So as a result of that, we shall get angle 1 equal to angle 3 plus angle 4, because this angle 1 is the exterior angle for this triangle. Now similarly, let us now look at the triangle ADF, this bigger triangle ADF. Upon this, we again apply the external angle property. Then we shall get angle 3, which is the external angle for this triangle, to be the sum of angles 2 and 5. Now let us add these two equations together. This angle 3 will get cancelled out, and we shall get angle 1 equal to sum of angles 2, 4 and 5. What we wanted to find is the sum of angles 4 and 5. So we keep them at one side. So we get the resultant as angle 1 minus angle 2, which means the angle 1 was angle BCD and angle 2 was angle BAD. So the result of addition of these two angles is same as the difference of these two angles BCD and BAD. So that matches the option A over here. So that will be reported as the correct answer. This is a mathematical aptitude question. It is saying that in a party, 60% of the invited guests are male and 40% are female. So let us assume that in a party there are 100x guests which are invited. Out of them there will be 60x male and 40x females. Now they are saying if 80% of the invited guests attended the party and if all the invited female guests attended, which means that out of these 100x people, only 80x people actually showed up for the party, and out of these 80x, all the female guests had attended, which means the female population was 40x. So they are asking what was the ratio between males and females who attended the party. So if in total 80x people have attended and out of that 40x were females, then definitely there will be 40x males. So the ratio of males and females who attended the party is same 40x by 40x, or we can say 1:1, which means equal number of males and females had attended that party. Hence, the correct answer would be B, 1:1 ratio in which the males and females attended that party. This is a mathematical aptitude question which is saying that a wealthy philanthropist has decided to gift 750 rupees to each male senior citizen and 1000 rupees to each female senior citizen. And in together there are 300 eligible senior citizens for this prize. So let us assume there are M males and F females. The total number M plus F will be equal to 300. And he is giving out 750 rupees to each male senior citizen and 1000 rupees to each female senior citizen who are eligible for the award. However, only 8/9 of the eligible men and 2/3 of the eligible women have actually claimed the gift, which means only 8/9 of M and 2/3 of F have actually claimed the gift. We want to find out how much rupees did he actually give away in total. So how much he will give away in total would be 8/9 of M into 750 spent upon male population plus 2/3 of F into 1000 spent upon female population. This will be, we shall divide this by 3 to get 250. So that converts into 2000 by 3M plus 2000 by 3F. We take 2000 by 3 common and get M plus F over here. And we already know that the value of M plus F is 300. So this gives us 2000 by 3 into 300. 3 will get cancelled out and we shall get rupees 2 lakh in total. So that is the total amount that has been spent upon gifting the senior citizens in the city by the wealthy philanthropist. So the correct answer is option B, rupees 2 lakh. This question is based upon probability. It is saying that a six-sided unbiased die with 4 green faces and 2 red faces is rolled for 7 times, which means the probability of getting a green face would be 4 by 6 and the probability of getting a red face will be 2 by 6. Now this die is rolled 7 times. So we can say that out of these 7, the 6 outcomes would result in 4 faces being green and 2 faces being red, because each of those 6 sides is equally likely to turn up as an output. So among the first 6 throws, we are more probable to get 4 green and 2 red faces. But for the 7th roll, we can say that the one which is more probable is likely to come up, which means since among these red and green faces, the green one is having higher probability. So the 7th throw is more likely to result into a green color turning up. So out of these 7 faces, we are more likely to get 5 green faces and 2 red faces as the outcome. So option C is the most probable outcome of this experiment. That would be our answer. This is an engineering mathematics question based on determinants and matrices. We have a matrix A, which is the product of two matrices U and V transpose. This Vt is denoting the transpose of V. Both the matrices U and V have been given to us, and we need to determine the largest eigenvalue of the resulting matrix A. Now since U is a column matrix 1, 2 having the order 2 cross 1, and V is again a column matrix with order 2 cross 1, its transpose Vt will become a row matrix having the same values but with the order 1 cross 2. Hence the product matrix A, which is U into V transpose, will become this product, and it will be a 2 cross 2 matrix. So we will find the product as 1 into 1, 1, 2 times 1, 2, again 1 into 1, 1, and 2 times 1, which is 2. So this is our matrix A. Now we know that the eigenvalue of a matrix can be found using A minus lambda I equal to 0 for this matrix A. So let us calculate that. I will be a 2 cross 2 identity matrix, which will be like this, and we have to make this equal to 0. So this becomes 1 minus lambda, 1, 2, and 2 minus lambda equal to 0. So we now take its determinant, and that will be 1 minus lambda into 2 minus lambda minus 2. That has to be equal to 0, so I can write this equal to plus 2. This will now become 2 minus 3 lambda plus lambda square equal to 2. So this gives us lambda square equal to 3 lambda if we cancel out 2 from either sides, and that gives us two values of lambda, that is 0 and 3. Now since we have been asked for the largest eigenvalue of A, out of these two we will go for 3, which is the larger one. Hence the largest eigenvalue of the matrix A is 3, and that is our answer.
The post-order traversal of a binary tree is 8, 9, 6, 7, 4, 5, 2, 3, 1. The in-order traversal of the same tree is 8, 6, 9, 4, 7, 2, 5, 1, 3. The height of a tree is the length of the longest path from root to any leaf. The height of the above tree is dash. So in this question we have been given the post-order traversal as well as the in-order traversal of a binary tree as these two, and they are asking us what is the height of the tree. So first we need to construct this tree based on this information, and then we need to find out the height from this tree, and I will show you how to do that. So if you are given a particular tree, the post-order traversal of this tree would be like this. First we print out the left subtree, and then we print out the right subtree, and then the root node will be printed. This is how the post-order traversal is. And in in-order traversal, we will print the left subtree first, and then we will print the root node, and then we will print the right subtree. So this is the post-order traversal. If you see in post-order traversal, the last element printed will always be the root node. So we can clearly say that 1 will be the root node for this tree. And after that, locate 1 in the in-order traversal of this tree, that is here, and 3 is given on the right side. So in in-order traversal, whatever is on the right side of something printed will be the right subtree. So we can say that 3 is the right subtree here. I mark 3 as well. So when we look in the post-order traversal, we have already printed 1, we have already printed 3, and the rest of the tree, this will be the left subtree. and in left subtree we are seeing 2 is printed last, so 2 will be the root of the left subtree. So I will write that directly here. And then I will locate 2 in the in-order traversal, which is here, and 5 is printed to the right side of true, so that will mean that 5 will be the right subtree of the node having value 2. So I can write 5 directly here. So these are printed, 2 and 5 is also printed, and again when we repeat the process we see 4 is coming here, that will be the root of the left subtree. We will locate 4 here, 7 is on the right side, so 7 will be the right subtree for 4. Again doing the same thing, we'll see 6, 9 is to the right, after 6 and 9 it's only 8. So this is the tree that is asked in the question, and they are asking us what the height of the tree is. So here the height definition is given. Height is the length of the longest path from root to any leaf. So clearly in this tree this is the longest path. In the longest path there are 5 nodes, that means the path length will be 4. So 4 is the answer. Two people P and Q decide to independently roll 2 identical dice, each with 6 faces numbered 1 to 6. The person with the lower number wins. In case of a tie, they roll the dice separately until there is no tie. Define a trial as a throw of the dice by P and Q. Assume that all 6 numbers on each dice are equiprobable and that all trials are independent. The probability that one of them wins on the third trial is dash. So in this question, they have given us a game which is played by 2 players, in which both of them are rolling a dice, and once they roll a dice, if both get the same number it will be a tie, and if they get different numbers it will be that the person with the lower number wins. So in this question, the probability that both of them roll the same number is that it will be 6 by 36, that is 1 by 6. How we got this is that when 2 players are rolling 2 dice, there will be 36 cases, which is 6 into 6, and the number of cases in which both will be same is 6, which is given as both roll 1, both roll 2, etc. Both of them roll 6. There are 6 cases out of 36, so the probability for a tie happening is 1 by 6. Similarly, the probability that different numbers are rolled is 1 minus 1 by 6, that is 5 by 6. So in the question they are asking us what is the probability that one of them wins on the third trial, which means that in the first and second trial it should be a tie between those two, and in the third trial it should be that one of the player wins. So the probability for that is, in the first trial the probability that both it will be a tie is that 1 by 6. Similarly in the second trial also it should be a tie, the probability for that is also 1 by 6. Similarly in the third trial it should not be a tie, it should be that one person wins, the probability of that is 5 by 6. So the probability of this happening is a product of these 3, which is nothing but 0.023, and that's the answer. In an entity relationship model, suppose R is a many-to-one relationship from entity set E1 to entity set E2. Assume that E1 and E2 participate totally in R and that the cardinality of E1 is greater than the cardinality of E2. Which of the following is true about R? So this is a question from DBMS, and they are asking us about ER models, particularly many-to-one relationship. So we have been given a particular relationship for 2 entity sets E1 and E2, and they are given 4 statements, and they are asking which one of these is true. So in this question the important points is that it is a many-to-one relationship and that the entities E1 and E2 participate totally in this relationship. And also regarding cardinality, they have given that the cardinality of E1 is greater than the cardinality of E2. Based on these, we can draw this following ER diagram for this relationship. If you don't know how to draw ER diagrams, you can refer to the video lectures and get an idea of this. So I have marked it is an M2-1 relationship and that both are participating totally. That is why this double diagram is there. So since both participate totally, we will know that for each entity in E1 or E2, there will be at least one in the other set, since both are participating totally. And if you look here, the one is marked on the E2 side. which means that for every entity in E2, there will be at least one entity in E1. There can be more than one, since it's a many-to-one relationship. That is marked here. And also for every entity set in E1, there will be exactly one in E2, since it's a one-to-many relationship. That is marked here. So based on this information, if you look at the options, there's only one which is correct. That is option A. Consider a process executing on an operating system that uses demand paging. The average time for a memory access in the system is m units if the corresponding memory page is available in memory, and d units if the memory access causes a page fault. Average time taken for a memory access in the process is x units. Which of the following is the correct expression for the page fault rate experienced by the process? So this is a question from operating systems regarding the virtual memory concept. So what they are asking us is to find out the page fault rate based on the data given here. So if you refresh the formula for average memory access time is hit rate when the page is available in memory. So that will be hit rate into the access time from memory plus fault rate, that is the rate when it is not available in memory, multiplied by the access time when it is not there. So we need to access from disk. This is also called the page fault service time. So in question they have given that memory access time is x and the access time from memory is m units, and the access time from memory when it is not there in memory, its access time from disk is d units as given in the question. So let us assume that the fault rate is p. In that case the hit rate would be 1 minus p. So substituting the values we know to the formula here, we will get that x equal to 1 minus p into m plus p into d. On solving this for p, we will see that p equals to x minus m by d minus m, which is option B. Consider a long-lived TCP session with an end-to-end bandwidth of 1 Gbps. The session starts with a sequence number 1, 2, 3, 4. The minimum time before this sequence number can be used again is dash. So this is a question from computer networks. They are asking us about TCP in this question. So what we are given is that for a TCP session we start with the sequence number 1, 2, 3, 4, and they are asking us what is the minimum time after which the sequence number will be used again. So in TCP sessions, for every packet sent there will be a sequence number associated with it. So the sequence number is a 32-bit number, and also for every packet sent, for the next packet the sequence number will be the initial sequence number plus whatever was the size of the previous packet sent in bytes, meaning that for every byte of data sent we will be having a unique sequence number. So one sequence number can be used for only one byte of a data, not one packet entirely. And they are asking us what is the time after which the sequence number will start repeating, so which is nothing but the wraparound time of TCP sessions. You can refer to the lecture videos to get more idea about wraparound time. So basically wraparound time is the time after which the TCP will be reusing the sequence number, which is nothing but the total data that can be sent with the available sequence numbers divided by bandwidth of the TCP session. So the total data that can be sent with the available sequence number is the total sequence numbers available, which will be 2 raised to 32 since it's the 32-bit number, into 8 bits. That's because for every byte we have a sequence number and one byte will contain 8 bits. Divided by bandwidth. Bandwidth in the question is given as 10 raised to 9 bits per second. So on solving this we will get 34.35. In the question they are asking us the time in seconds rounded to the closest integer. For 34.35 the closest integer is 34. So the answer to this question is 34. A 32-bit wide main memory unit with a capacity of 1 GB is built using 256 MB by 4-bit DRAM chips. The number of rows of memory cells in the DRAM chip is 2 raised to 14. The time taken to perform one refresh operation is 50 nanoseconds. The refresh period is 2 milliseconds. The percentage of the time available for performing the memory read or write operations in the main memory unit is dash. So this is a question from digital logic. In this question they are asking us about DRAM chip refreshals. So in dynamic RAMs we need periodic refreshals to maintain the charge in it. Without it the data would be lost. So in this question they have given us that the time taken to perform one refresh operation is 15 nanoseconds, which is nothing but the time taken to refresh one row in the DRAM chip. So whatever information regarding the size is not relevant to solve this question. So they have given us that the time taken to refresh one row is 50 nanoseconds, which is 50 into 10 raised to minus 9 seconds. And the number of rows is 2 power 14. The total time taken will be the number of rows multiplied by the time to refresh each row. On calculating this, we will see that it is 0.819 milliseconds. They have given us that the refresh period is 2 milliseconds. So every 2 milliseconds this refresh will happen. So the percentage of time spent in refreshing is 0.819 by 2, which is nothing but 40.9%. Therefore the percentage of time for read write is 59.1%, which is 59%, rounding it to the closest integer, and that is the answer. The chromatic number of the following graph is what? So we have been given a planar graph here. They want to know the chromatic number of this graph. So chromatic number of a graph is the minimum number of colors we need to use in order to color each nodes in the graphs, such that no two adjacent node will be getting the same color. You can refer to the graph theory lecture videos to get more idea on this. So here they have given us a planar graph, and every planar graph can be colored using 4 colors. 4 is the maximum number of colors we will need to color this graph. This we know already, and this is a pretty small graph, so we can try coloring this and see how many numbers are actually needed, how many colors are actually needed. So if you look at this, these 3 nodes form a fully connected component. Each of these nodes are connected to the 2 other nodes, so we will need at least 3 colors in order to color this part. So I will give the colors as following: 1, 2, 3. Now we will start coloring the rest of the nodes such that no 2 adjacent nodes have the same color. Here we have 3 and 1, so this we can give 2. And D is connected to just 3 and also 2, so D we have to give 1 here. F is connected to 1 and 2, so F should be 3. So clearly we can color this graph using 3 colors. 3 is the answer. This is a match the following type question coming from computer networks. They have given us different fields in each protocol and they are asking us the length of each of these. So we will go through these one by one. One is UDP headers port number. In TCP and UDP both, the port number is 16 bits, so this will be 4. Ethernet's MAC address. MAC address is a 48-bit field. So we'll match it here. TCP header's sequence number. In TCP header, the sequence number is always a 32-bit field, so this will be this. IPv6 next header. Next header is a field in IPv6 header part, so and that is 8 bits. So P is 4, Q is 1, R is 2, and S is 3. This is the answer. See. This is a question from data structures. A queue is implemented using a non-circular singly linked list. The queue has a head pointer and a tail pointer as shown in the figure. Let n denote the number of nodes in the queue. Let nq be implemented by inserting a new node at the head, and dq be implemented by deletion of a node from the tail. Which of the following is the time complexity of the most time efficient implementation of nq and dq respectively for this data structure? So we have been given this singly linked list, and they are asking us what's the complexity of performing NQ and DQ to this linked list. So they have given that for NQing we do it by inserting a new node at the head. So what we need to do for NQ is, this is the head here, we need to add a new node here. So this we can easily do by creating a new node we have the head pointer. We will, using the head pointer, we'll know the address of this node. So we'll put the next address as here and we'll change the head pointer to here, that is NQ. So clearly the complexity is theta of 1 only. Let's take a look at DQ now. DQ is implemented by deletion of a node from the tail. So this is the tail here and we need to remove this node. So after removing this node, there will be a second last node here. We will need to reassign tail to this node. But using tail only, we don't know the address of this node. Like we don't have the address. Now to find this address, this is a singly linked list. So from this node, we can't go to this node. So the only way of getting the address of this node is we need to go to head and we need to traverse one by one and we need to come to this node. There is no other way to get the address of this node. So for doing that, this will take theta n time to get this. So dequeuing at tail will take theta n time. So this is the right answer, B. NQ is theta 1, DQ is theta n. Consider a system with 3 processes that share 4 instances of the same resource type. Each process can request a maximum of k instances. Resource instances can be requested and released only one at a time. The largest value of k that will always avoid a deadlock is dash. This is a question from operating systems, specifically the deadlock section. Here they are saying that we have a system with 3 processes and we have 4 instances of the same resource type, and each process can request a maximum of k instances. They are asking what's the largest value of k that will always avoid a deadlock. So we have 3 processes, 4 resources, and the maximum demand is k resources. Now let's try assigning these resources to each of the processes such that each of the processes is taking up 1 less than the maximum demand. The maximum demand is k. So 1 less than maximum demand is k minus 1. Let's assign k minus 1 resources to each of the processes. That will take up a total of 3 into k minus 1 resources. Now the condition to avoid deadlock is the number of resources should be 1 greater than the 1 less than maximum demand of assigned to each of these processes. That is 1 less than maximum demand assigned to each of the processes 3k minus 1. We need additional 1 more resource to always avoid a deadlock. So the number of resources required to avoid a deadlock is 3 into k minus 1 plus 1. That is 3k minus 2. Now we know that we have 4 instances available. So equating that to 4, 3k minus 2 should be less than or equal to 4. Solving that, we will get k should be less than or equal to 2. 2 is the answer here. I'll also show you how we got to. Let us say k is 1. That means each process will ask only 1 resource. We have 3 processes. We'll assign 1 resource to each of these. Already the maximum demand is met. We still have 1 more resource available which no one will be using. This will never cause a deadlock because 1 resource is requested which we assign and then that process is over. If k is 2, let us assign 2 minus 1, that is 1 resource to each of these processes. 3 resources are used up. We have 1 extra resource available. Any of the process can request this, but once that is assigned, let us say 1 is requesting this, 1 got assigned to, maximum demand is met, so 1 will run and then these 2 resource extra will be available which 2 or 3 can again request. So again here also there is no deadlock. If k is 3, we will see that there are 3 processes. Let us say 1 took up 2 resource, 2 used 1 resource, 3 used 1 resource, already 4 resources are used up and the maximum demand is 3. So 1 can still request, 2 can still request, 3 can still request. All 3 are requesting actually and there is no resource available. So it's a deadlock, no one can proceed. So that's how k is 2. Consider the following statements regarding the slow start phase of the TCP congestion algorithm. Note that CWND stands for the TCP congestion window and MSS denotes the maximum segment size. So this is a question from TCP congestion control algorithm coming from computer networks section. Please refer to the lecture videos in the TCP section to understand how the TCP congestion control works. So I'll basically explain how it goes. Initially what we have is, for TCP congestion control we will be having 3 phases. One is the slow start phase, then we have the congestion avoidance phase, and then we have the congestion detection phase. So what happens in slow start phase is we will be sending 1 packet. After we receive the ACK, that is 1 round trip time, we will be sending double of that. Similarly, after each act we will be doubling it again. So that goes on, so we will be having exponential growth in this phase. After that we have the congestion avoidance phase. Here what happens is after each round trip time we will be increasing the congestion window by 1. And similarly, once it reaches the threshold here, we have the congestion detection phase, that is, it is stable now. After each round trip time the congestion window doesn't change. So the question is about the slow start phase. So how it works is, initially we have one packet, that is one MSS. We will be sending that. Once we receive the ACK, that is after the round trip time, we will double it. Then we will be sending 2 packets. Again after the round trip time, we will be doubling it again. So we will be sending 4 packets here. So clearly you can see that after every round trip time, the congestion window is doubling. Initially it was 1, then it was 2, then it was 4. So from here, option 4 is correct. The congestion window approximately doubles every round trip time. So how TCP actually achieves this is, after we receive every ACK, we are increasing the congestion window by 1 MSS. So initially you can see it is 1. After we receive 1 ACK, we made it 2 and we sent 2. Here we will be receiving 2 ACKs now. Now here we are sending 4. So before 4 we have received a total of 3 ACKs. And similarly, after this round trip time, we will be sending 8. And total packet sent already was 7. So we need to receive 7 ACKs before sending 8. So clearly you can see that after every ACK, that window is being increased by 1. So there is none of the options here which is correct. Here it's saying congestion window increased by 2 MSS, that is false. Approximately doubles on every ACK, that's also false. It doubles on every round trip time. Increases by 1 MSS on every round trip time, that's also false. It increases by 1 MSS after every ACK. So only 4 is the correct answer. This is a question from compiler design topic. They have given us 4 statements regarding compilers and they are asking which of the following statement is false. Let's take a look at the statements. A. Context-free grammar can be used to specify both lexical and syntax rules. This is true. Context-free grammar, in a program, context-free grammar can be used to specify both the syntax rule, that is how the syntax of the program should appear, and also the lexical rule, that is defines how the token should be appearing. So both is true, both can be given by context-free grammar. So this is correct. Type checking is done before parsing. This is false. Type checking happens in the semantic analysis phase of the compiler, whereas parsing happens before that. So this is the false statement, so this is the correct answer. We'll look at the other 2 as well. High-level programs can be translated to different intermediate representations. That is true. Whatever part of the compiler is reading the intermediate representation, we can have multiple intermediate representation. That is true. Arguments to a function can be passed using the program stack. That's also correct. That's how we pass arguments to a function. We push the return address first and then we'll push the arguments and then we'll call the calling function. That's how it passes. So C and D is also true. B is the answer. Let n be an NFA with n states. Let k be the number of states of a minimal DFA which is equivalent to n. Which of the following is necessarily true? So this is a question from TOC regarding NFA and DFA. So this is actually an easy question, but it's also a tricky question. Many students will see NFA and DFA and they'll think that DFA should have less than or equal to the number of states of NFA, and people can wrongly mark B, but B is wrong here, which I will show you here. Consider the language A star and consider this NFA. This NFA has 3 states actually. And the minimal DFA for the same language needs only 1 state. Here you can see that these 2 states are actually unnecessary, but still we can design an NFA like this. So saying that k is greater than or equal to n is wrong. And they are asking us which of the following is always true. So the correct answer is actually k is less than or equal to 2 power n. That's because for every NFA, we can always construct a DFA which will have the number of states which will be the power set of the number of states of this one. The power set will contain 2 raised to n states. So k, that's the number of states in the minimal DFA, will always be less than or equal to 2 power n. For the proof of that, you can refer to the lecture videos from TOC. The following are some events that occur after a device controller issues an interrupt while process L is under execution. Which of the following is a correct order in which the events above occur? So this is a question from computer organization. They are asking us about interrupts. They have given us 5 events and they are asking what's the right order in which these events occur when an interrupt is issued to an OS. So I have marked the events which occur in the correct order. So when a process is executing and an interrupt is issued, the first what we need to do is we need to finish executing the current instruction in the process. After that, we need to push the process status onto the stack so that we can retrieve it later and we can rerun the process. After doing that, we need to load the program counter for the interrupt service routine. After we load the program counter, we will start executing the instruction in the interrupt service routine. After that, after the interrupt is complete, we will come back and pop the process status to resume running. So I have mapped these events to the correct option and we can see that the right answer is QPTRS, which is option A. That's the answer. Let XOR and XNOR denote exclusive OR and exclusive NOR operations. Which of the following is not correct? So in this question they have given us 4 statements regarding XOR and XNOR and they are asking which of the following statement is false. So here I have given the truth table for XOR and XNOR. You can take a look at this if you are unsure. We'll take a look at this last statement. Here the LHS is P XOR P complement XOR Q. Now whatever the value of P is, it will always be 1 XOR 0 or 0 XOR 1, which is the same, which will always be 1, making this statement nothing but 1 XOR Q. Now 1 XOR anything is a complement of that. You can verify that from the truth table here. So 1 XOR Q is Q complement. If you take a look at the RHS part, it is P XNOR P complement XNOR Q complement. Again similarly, XNOR of P and the complement of it will always be XNOR of 1 and 0, which is always 0, which we are doing XNOR with Q complement. Now 0 XNOR Q complement, when we do XNOR with 0, it will be the complement of this part, which is nothing but Q. So in LHS we got Q complement, RHS we are getting Q, so this is the wrong answer. You can draw the truth table for statements A, B, C and find out that these are all correct. They are asking which of the following is not correct, so D is the answer. Let G be a finite group of 84 elements. The size of the largest possible proper subgroup of G is dash. So this is a question from set theory from engineering mathematics. This is a direct application of Lagrange's theorem here. Lagrange's theorem states that for any group G with order n, every subgroup H has order k such that n is divisible by k. So if you don't understand Lagrange's theorem, you can refer to the lecture videos on set theory and algebra. So this clearly, from this we know that the order of the subgroup should be dividing 84, which means that the order of subgroup has to be one among these. These are the factors of 84. And in the question they have clearly given it's a proper subgroup, so it can't be G itself, meaning it can't be 84. So the next largest one is 42 and 42 is the answer. Which one of the following is a closed form expression for the generating function of the sequence an, where an equal to 2n plus 3 for all n equal to 0, 1, 2, etc. And we have been given these 4 options. So we have been given the generating function for the sequence and we need to find out the closed form expression, which among these 4 it is. So we'll try to do that. In order to answer this question, you need to know the binomial expansion for all these. So I'll read it out. 1 plus x all raised to minus n equal to 1 minus nc1 x plus n plus 1 c2 x square minus n plus 2 c3 x cube, etc. So substituting x with minus x here, we will get the same for this one. 1 minus x all raised to minus n. That is 1 plus nc1 x plus n plus 1 c2 x square plus n plus 2 c3 x cube, etc. Now substituting for n minus 1 and minus 2, I'll get these 2 expressions. So these 2 expressions we need to know beforehand in order to answer this question. Now let's try to answer this. They're asking the closed form expression. So closed form expression is given by sigma n equal to 0 to infinity an x raised to n. Now an is 2n plus 3, so we can rewrite it as n equal to 0 to infinity 2n plus 3 x raised to n. This I can separate into two sigma series. One is sigma n equal to 0 to infinity 2n x power n plus this 3 I can take it out, 3 into sigma n equal to 0 to infinity x power n. Now we can try writing n 0, 1, 2 etc. Then we will get this following sequence for this sigma part, and then we will get 3 into this sequence for this sigma part. Now from this sequence you can see that 2x is common in all of these, so I will take 2x outside. So this can be written as 2x into 1 plus 2x plus 3x square etc. plus 3 into 1 plus x square plus x3 etc. So this sequence is nothing but 1 minus x all raised to minus 2, and this sequence is 1 minus x all raised to minus 1. So I can directly substitute that here, which will give me 2x by 1 minus x the whole square plus 3 by 1 minus x. Solving for this, I will see that it is 3 minus x by 1 minus x square, which is option D. This is a question from theory of computation, and they are asking us about closure property of various languages. So the set of all recursively enumerable languages is what? They have given 4 statements and they are asking which of these is true. We will analyze these one by one. A, closed under complementation. This is false, because for a language belonging to recursively enumerable, if the complement is also recursively enumerable, then that will mean that both of those will belong to the recursive part. That is wrong. This is not complement. This is not closed under complementation. Complement of L belong to recursive enumerable, won't be recursively enumerable. So this is false. We'll take a look at C, saying that it's a subset of all recursive languages. That's also false. This is the set of all recursive languages, and recursive enumerable languages set is this. Recursive is a subset of recursive enumerable, not the other way. So this is also false. D, an uncountable set. That's also false. The set of all recursively enumerable languages will be a countable infinity. Why that is so is that for every language belonging to this set, we can have a Turing machine associated with it. Any Turing machine will have an encoding in 0, 1 format, which is nothing but a language belonging to epsilon star, where epsilon is 0, 1. So the proof of this, you can refer to the lecture videos for theory of computation, the Turing machine section, and this will be proved there. So this is also false. So B is the correct answer. Any languages are closed under intersection. Consider the sequential circuit shown in the figure, where both flip-flops used are positive edge triggered D flip-flops. The number of states in the state transition diagram of this circuit that has a transition back to the same state on some value of in is. So this is a question from sequential circuits in logic design. Here we have been given this particular design using two D flip-flops. So the property of D flip-flop is that whatever we give as input, that will be the output after one cycle. Meaning whatever we give as input will be coming out of this one, and whatever is the value of this will be coming out of this flip-flop after one cycle. For convenience, let us name this one Q0 and this one Q1. Each D flip-flop can take either of two values, that is 0 or 1. Here there are two flip-flops, meaning there can be 4 states in total, that is 0, 0, 0, 1, 1, 0 or 1, 1. Also input can have two values which will be 0 or 1. Based on this, I have drawn the table for transitions here. These are the states and the corresponding input, the value of Q0 and value of Q1. So if you look at the circuit, since these are D flip-flops, after every cycle, whatever is the value of Q0, that will be coming as input to this one. So the value of Q1 in the next cycle will be whatever is the value of Q0. Similarly, whatever the value of Q0 after each cycle will be whatever is input, since both of these are D flip-flops. So we need to find out what is Q0 next and Q1 next after each cycle. So like I said, whatever is input, that will be coming as Q0 in the next cycle. Also whatever is in Q0, that will be coming out as Q1 in the next cycle. So we can directly write input here in Q0 table 0, 1, 0, 1, just like that I have written here. Also Q0, just like this I have written here as the next cycle. 0 0 0 0, just like that I have written here. Now we'll try drawing the state transition diagram based on this information. We have 4 states, 0 0 0 1 1 1 and 1 0. Let's take a look at the first state. Initially it is 0 0. On input 0 it is going to this state as shown here, 0 Q0 and Q1x 0 0. So on input 0 we will move from 0 0 to 0 0. That is given by this line. So just like that, from each state, for each input I will find out which is the next state, and in this diagram we can draw correspondingly. So this is the state transition diagram we will get at the end. And the question is number of states that has a transition back to the same state. So they are asking us for transitions which is from one state to the same state. If you look at that, there are only 2 transitions like that here. In 0 0, on value 0 we follow this path and come to the same state. On input 1 1 also we have one more transition. Similarly on input 1 we come back to the same state. The rest of the transitions on input we are moving to some other state. So there are only 2 states which has a transition back to the same state. So the answer is 2 for this question. The value of integral 0 to pi by 4 x cos x square dx correct to 3 decimal places is dash. We have been given this integration expression and we need to find the value of this. There are various ways to solve it, but if you take a look at this, we will see there is an x square expression within cos. So we can try substituting x square to some other variable and see what happens. Let x square equals t. On taking derivative, we will see 2x dx equal to dt. In the expression we can see the form x dx, which is same as this. So we can proceed with this. When x is 0, the value of t, which is x square, will also be 0. Similarly, when x is pi by 4, t will be pi square by 6. So we can rewrite this expression as this in terms of t. Integral 0 to pi square by 16 cos t dt by 2. Since 2x dx is dt, x dx will be dt by 2. On solving this, we will see that cos t integral of this is sin t. So this is the answer. Evaluating this, we will see it is sin pi square by 16 minus sin of 0, which is this, and the answer is 0.2889. Consider the following 2 tables and 4 queries in SQL. This is table 1, this is table 2, and the queries: select b.isbn, s.copies from book B, inner join stock s on b.isbn equal to s.isbn. Query 2, 3 and 4 are also exact same queries, except that in first one we have inner join, in 2 we have left outer join, 3 we have right outer join, and on the query 4 we have full outer join. The queries are same except for these parts. Which of the queries above is certain to have an output that is a superset of the outputs of the other 3 queries? So we have been given these 4 queries and they are asking, on taking the output, which of the queries guaranteed to have an output that is a superset of the output produced by the other 3 queries. So for answering, we just need to know the properties of inner join, left outer join, right outer join and full outer join. So consider that these are the 2 tables. In book, let us suppose that we have ISBN values 1, 2 and 3 available. And in stock, let us suppose we have ISBN values 2, 3 and 4 available. So as you can see, this 2 and 2 is matching, this 3 and 3 is matching. And on the query they are asking, we are doing a join based on the ISBN values, at b.isbn equal to s.isbn. So if you take an inner join, it will only print the output where this join value is available in both the tables. So inner join will only print the rows from the tables where for the values of 2 and 3 only. For 1 there is no matching value here, for 4 in this table there is no matching value here. Similarly in left outer join, we will take inner join, and then for whatever values in the left table is there, even if the value is not available on this, we will print that row, except that in this table there are no values for 1 available. So this s.copies will just print it as null. So left outer join will be printing 1, 2 and 3. Similarly, on right outer join, we'll take inner join, so 2 and 3 rows would be there. Additionally, this 4 value from the right table will also be there. In the corresponding column here, we'll be printing null value only, since there is nothing matching for 4. So right outer join will give 2, 3 and 4. Full outer join will take the values from both the table regardless of whether there is a matching value in the other table, and for whichever there is matching, it will show the corresponding match. So for full outer, it will print 1, 2, 3 and 4. Clearly full outer will always be a subset of the other 3. So this is the right answer. So query 4 is the answer. This is a C programming question. In this code snippet, we have been given a global variable counter which is initialized to 0. And we have this function calc, and from main we are calling calc 4,81, and then asking after this executes, we are printing counter. So what will be the value of counter after this? So counter is a global variable here, and inside the calc function we can see that immediately counter is being incremented. So since it's global and there are no other counters defined inside, this will be the one that is getting incremented here. So we look at this function. Initially we are calling it with 481. So we are calling calc 481. So immediately counter will be incremented after this. So here only if b equals to 3, then we are returning immediately. Otherwise we will call the same function again with values a and b by 3. So here initially b is 81, which is not 3, so we will call calc again with 427. Again we will increment the counter immediately. Since b is not 3 now, we will call calc 4,9 again. Here also counter is incremented, and inside that also, even now b is not 3, calc 4,3 is called. Again counter will be incremented. Now we are calling calc 4,3. Since b is 3, it will return from here. After returning, we will come to this statement in the calling function above. Here also you can see immediately we are returning. So from each function we will return immediately one by one. Counter is incremented 4 times in total here. So when we are printing here, the value will be 4. Consider the following processor design characteristics. 1. Register to register arithmetic operations only. 2. Fixed length instruction format. And 3. Hardware control unit. Which of the characteristics above are used in the design of a RISC processor? So this is a question from computer organization. A RISC processor means a reduced instruction set computer. So if you don't know about RISC and CISC, you can refer to the lecture videos for computer organization, and you can get all the properties there. So the property of RISC is that it will always have a fixed length instruction format. So 2 is definitely correct. And it will always be hardware, since it needs to be faster. So hardware is also correct. And the first one is register to register arithmetic operations. So that is also true, because for any arithmetic operation we can't directly perform read or write from memory and then do operations there itself. It has to be in register. So register to register arithmetic operations only is also correct. So there were 4 options given here, so all 3 was the right answer for that. In this question, we have been given a C program, and they are asking us to find out what the output of the program is. So here we have a structure named outNode defined, which has 3 character elements x, y and z. And in main we are defining outNode p equal to these. So x will be character 1, y will be char 0, and z will be a plus 2. When we write a plus 2, a will be typecast to int, whose value will be 90 something, plus 2, so it will be the integer value of character c, and then again we are storing it in char c, so the typecast back to char will happen here. So actually what is stored in z will be character a and incremented by 2, which is nothing but character c. So in x, y, z, in p, x will be character 1, y will be character 0, and z will be character c. And here we are defining a pointer q pointing to p. So q will be pointing to c. In this print statement, you can see that everywhere we are typecasting q to char star. When q is pointing to p, char star of p will be pointing to nothing but the first character in the struct p, which will be x. So char star Q will be pointing to the X and star of that will print this character 1. So here we are printing two characters %C, comma %C. First will be char star Q plus 1. So char star Q plus 1 will be nothing but Y. Q is pointing to X, Q plus 1 will be pointing to the next element, that is Y. And then we have a star outside here, so which means the value of that will be printed here. So here it will print 0. It will be printing just 0 without any quotes. And the second one is char star of Q plus 2. Q plus 2 will pointing to Z and we are taking a star here outside, so it will be printing C. So 0 comma C will be the answer here, that is option A. But without even solving you could have answered it, because always it is printing %C comma C. It will be some character comma some character. There won't be any quotes like this, or in option B there will be a plus. It won't be, it anyway won't be printing this plus character. So we could have directly said that B, C and D were wrong even without solving the question. The size of the physical address space of a processor is 2 raised to p bytes. The word length is 2 raised to w bytes. The capacity of cache memory is 2 raised to n bytes. The size of each cache block is 2 power m words. For a k-way set associative cache memory, the length of tag field is dash. So this is a question from computer organization. They are asking us about cache here. So we'll assume that the memory is byte addressable. So we'll be mapping the physical address space and the cache address both here. It is saying the physical address space is 2 raised to p bytes. So this entire thing length would be p. So word length is 2 power w bytes. So that we can map at the rightmost end of the address. These are each physical address. So the rightmost end would be the word length. And the capacity of the cache memory is 2 power n bytes, meaning that this entire block will be n. And similarly, the rightmost part would be word w. And then they have given us that it is a k-way set associative cache memory. Also the size of each cache block is 2 power m words. So each cache block is 2 power m word, means for denoting the block we need additional m bits, which will map here and here similarly. It's given that it's a k-way set associative memory. So from the rightmost end of the cache address we'll need to take log to the base 2 of k here. So this much part will denote the set number. This I can map directly like this to the physical address space. So this is how a k-way set associative map looks. For each cache block we have one tag field here. So whatever this tag field should provide us is that this leftmost end of the physical address should be there in the tag field, and also it should provide these many bits for a k-way set associative map. Since let us say it is a 3-way set associative map, then that means in this there can be 2 power 3 lines, that is 8 lines, meaning to this tag bit we need to add 3 additional bits so that that particular block can reside anywhere in this. Please take a look at the lecture videos for set associative maps to understand this. So on mapping this directly here, I will see that this much part of the physical address place plus log to the base 2 of k, this much is needed for tag bits. Once I get the tag bits from the address itself, we can identify the set number, the block number and the word also from here. So clearly this part is nothing but p minus n, and this is log to the base 2 of k. So the final answer would be p minus n plus log to the base 2 of k. Also there is a formula given in the lecture videos for set associative mapping. The tag bits would be the main memory size in bits minus the cache size in bits plus how many bits are needed for that for denoting k-way set associative, that is log to the base 2 of k. So directly also you could have answered this. We were given 4 options and this is the correct one, B. This is a C programming question. we have been given this code snippet and they are asking us what the output is, and we have been given 4 options as well. So we have 2 functions here, fun1 and fun2. Both of these are performing swapping within this function. If you see, we have 2 parameters s1 and s2 passed, and it is performing swapping to these 2. So at the end of this, whatever is in s2 will be in s1 and whatever is in s1 will be in s2. The same is there for fun2 as well, only that the data types are different. So inside the main function, we are defining car star str1 equal to high and car star str2 equals to by. Initially we will call fun1 and then print the values, and then we will call fun2 with the address of these, and we will be printing the values, and we need to find the output. So here we are defining car star str1 equal to high, str2 equal to by, which means inside str1 we will be having a value which will be the address of wherever this string is stored. So the value inside str1 will be 1000, let us say, meaning that 1000 will be the address from where the string high will be stored. Similarly, inside str2 there will be a value which will be the address of wherever the string by is stored, and these variables itself will have its own address. Let us say str1's address is 100 and str2's address is 200. This is the address of the variable. What is stored inside is the value, which is address where the string is stored. So initially in fun1 we are doing pass by value of str1 and str2. So whatever is inside str1 and str2, 1000 and 2000 will be passed here, and they are performing swapping inside this. So whatever is in s1 and s2 will be swapped, but we were passing what the values inside str1 and str2. You are not passing the address. So even after the swapping, whatever is inside str1 and str2, that doesn't get changed. str1 and 2 will still have 1000 and 2000. So when we print, you will be printing whatever was the value earlier, that is high, and str2 will print by. Whereas in this case we are passing the address inside, we are doing pass by reference. So we are passing the address of str1 and str2. So address of str1 and str2 becomes s1 and s2 here, and then we are performing the swap. Since it is passed by reference, after performing swap, the values inside this will also get swapped. So after fun2, these values will get swapped actually, meaning that when we are printing str1 and str2, it will be swapped and it will be printing by and high respectively. So let's take a look at the options. Option A is the correct answer. Consider the following undirected graph G. Choose a value of x that will maximize the number of minimum weight spanning trees of G. The number of minimum weight spanning trees of G for the value of x is. So in this question we have been given this particular graph in which the value of x is unknown. We need to give x some particular value and find out the number of minimum weight spanning trees. And the question they are asking is for what value of x this number of minimum weight spanning trees will be maximum, and what that maximum value will be. So we will try by assigning x value starting from 1. Let's assume x equal to 1. In that case, we need to construct the spanning tree. So by Kruskal's algorithm, what we will do is we will choose the edge with the smallest weight here. So that will be this edge. And the next would be this one. So both would be chosen. These are connecting different vertices. And next we will choose this edge starting with 3. And only this node is remaining now. Now there are 2 edges possible here. These 2 are having values 4. Whichever we choose, the minimum weight will be the same, meaning that we can choose any of these 2. We get 2 different graphs based on which edge we are choosing. That is, in this case there will be 2 graphs possible. Let us try by making it 2. Then also we will be getting the same graph. We will be choosing 1, and the second smallest will be this one. We will be choosing this edge, and then we will be choosing 3. Again, only in this edge we have to determine which edge we need to use. So we have 2 graphs possible here based on the edge we are choosing. And when we are choosing 3 also, we will be getting the same graph. This is 1, this will be 3, this will be 3, these 2 we are choosing, and these 2 edge any we can choose. We are getting the same graph. There are 2 possibilities here. Now let's try assigning 4. In this case, this edge we will be choosing, it is 1. The second smallest is this edge, it will be 3. and then we have to connect this node. We have two options. We can choose either 4 or 5. 4 is the smallest one. We will be choosing 4 here. And then for this node, again, we can choose one of these two. It's again the same graph. We have only two possibilities. Now we are getting some idea here. Only for this node, if we can introduce some non-determinism between this and this, if we giving an option here, maybe we'll get more graph. We'll try with 5 here. So when x is 5, we'll be choosing this one, that is the smallest. We take 1. Next, second smallest is 3. We choose this. And then coming, the smallest will be 4. We can choose either one of these two, and that will connect this node. After that, we don't have to choose the other node. Even though 4 is the next smallest value, we don't need it because it is connecting only the same nodes which is already there in the graph. Now we coming to this node, and this node we have two options here, 5 and 5. Again, we can choose any one of these two, meaning that for this node we can choose any one of these two, which gives two options. For this node also we can choose any one of these two, gives two options. So the total will be 2 into 2 equals 4. Now if you try with x values greater than that, if I give 6, I will only be choosing the node with value 5 instead of 6. So increasing the value, I won't be getting multiple spanning trees. So the answer is 4 when x is 5. A processor has 16 integer registers R0 to R15 and 64 floating point registers F0 to F16. It uses a 2-byte instruction format. There are 4 categories of instructions, type 1 to 4. Type 1 consists of 4 instructions, each with 3 integer register operand. Type 2 consists of 8 instructions, each with 2 floating point register operands. Type 3 consists of 14 instructions, each with 1 integer register operand and 1 floating point register operand. Type 4 consists of n instructions, each with a floating point register operand. The maximum value of n is. So this is a question from computer organization. They are asking us about machine instructions. Let's take a look at how we can solve this. So in the question, they have given us that it uses a 2-byte instruction format, which meaning that the size of the instruction is 2 byte or 16 bits. Therefore, the number of unique instructions it can have is 2 power 16. Now let's take a look at how much each type uses up. Now type 1 consists of 4 instructions, each with 3 integer register operands. Now there are 16 integer registers. Therefore, for representing each of the register, we will need to use 4 bits out of the instruction. And also there are 64 floating point registers. Therefore, for representing each register, we need 6 bits out of the instructions. So let's take a look at type 1. Type 1 consists of 4 instructions, each with 3 integer register operands, which meaning that total instructions will be 4 type 1 instructions into 2 power 4 each for each of the integer operands which we need to represent uniquely. Therefore, it will be 2 power 4 into 2 power 4 into 2 power 4 into 4 instructions, which is 2 power 14. Type 2 consists of 8 instructions, each with 2 floating point register operands. That means the total number of instructions will be of type 2 will be 8 into 2 power 6 into 2 power 6. 2 power 6 because we need 6 bits for representing floating point register. That adds up to 2 power 15. Similarly, type 3 is 14 instructions. It consists of 1 integer and 1 floating point register operand. So the total number of instructions will be 14 into 2 power 4 for the integer register and 2 power 6 for the floating point register, which is 14 into 2 power 10. So let's see how many remaining instructions are there. Remaining instructions equal to 2 power 16 minus the sum of type 1, type 2 and type 3 instructions, which when you solve, you'll see there is 2 power 11 instructions left. Now for type 4 instruction, each instruction has only 1 floating point register operand, and 1 floating point register operand needs 6 bits to represent. Therefore, the number of type 4 instruction, let us say it is n into 2 power 6. Now that will be equal to 2 power 11. Now we can solve for n easily here. We will see that n is 2 power 11 by 2 power 6, which is 2 power 5. The answer is 32. This is a question from engineering mathematics regarding matrix multiplication. So in the question, this question is very long, please go through it and understand. What they are explaining in the initial part is that they are explaining the concept called explicitly computed pair, which they are defining as in a given matrix multiplication chain. Let us say if this is the chain, then which all are multiplied initially in the first chain, like that is two matrices multiplying directly in the chain is called explicitly computed pair. That is, in this G1, G2, G3, G4, G5, G6 multiplication, only 2, 3 and 4 and 5, 6 are computed initially as the matrix in the original form. So these are the explicitly computed pair. So the question is saying that considering a matrix multiplication chain F1 to 5 with these matrices and these dimensions, in the parenthesization of F1, F2, F3, F4, F5 that minimizes the total number of scalar multiplications, the explicitly computed pairs is or are. So we want to parenthesize this matrix multiplication so that we will be minimizing the scalar multiplications. The operations for scalar multiplication is given here initially. If we are taking a matrix G1 of P by Q and G2 of dimension Q by R, then multiplying G1 by G2 takes PQR scalar multiplication. The definition is given here. So they are asking in the matrix chain multiplication that minimizes the scalar multiplications, which are the explicitly computed pairs. So there are two ways to doing this question. One is that we need to go through this matrix. We need to find out which is the parenthesization that will minimize the scalar multiplication, and from there we can look at options and get the answer directly. Or we can look at the options given here. There are only 4 options, and then we'll try out all 4 cases, and then whichever is minimum we can choose that. So I'll be going by that approach here. So these are the 5 matrices F1 to F5. Let us go through option A. Option A states that F1, F2 and F3, F4 are the only explicitly computed pairs. We'll write that. So F1 and F2 will give us the explicitly computed pair. F3 and F4 also will give it directly. And then we need to multiply F5. So there are 2 ways in which we can assign the brackets such that F1, F2 and F3, F4 are the only explicitly computed pair, which I have given here. We can either give F1, F2, F3, F4 and then multiply these 2 and then multiply F5 at the end. Or we can do F1, F2, F3, F4 and then multiply F3, F4 with F5, and then this total we multiply with F1, F2. We'll see the number of operations in each of these cases. F1, F2 will be taking 2 by 25 by 3 scalar multiplications, which I have written here. F3, F4 will take 3 by 16 by 1 scalar multiplication. This total matrix will be having a dimension of 2 by 3 by 1. And then multiplying these 2, we will be getting 2 by 3 by 1 scalar multiplications. Again multiplying it with F5, we will be getting 2 by 1 by 1000 scalar multiplications. So the total we will see that it is taking 2204 scalar multiplications in this case. We will look at this case. F3, F4 will be taking 3 by 16 by 1. F4 multiplied with F5 will be taking 3 by 1 by 1000. So clearly we can see that again we will have to multiply F5 at the end. Here itself it is taking 6000 scalar multiplication, which is way greater than 2204, and this 1000 part is coming twice also, so it's much greater than this, so we don't need to consider this one. So for option A, this is the lowest part we got. Now we'll look at option B. They're saying F2 and F3 only. Now F2, F3 only, there are 3 ways actually in which we can assign this. So we'll assign F2, F3 initially, and then one way is that we'll multiply F1 with this. After that we'll multiply F4 with this. After that we'll multiply F5 with this. Again, if I'm taking this scalar multiplication here, this part will take 25 by 3 by 16. This itself is greater than 1000. Again at the end, the final part, I will get 1000 by 1 by 2 here at the final part. This is anyway greater than the minimum we have got already. So this is also not correct. We'll look at the other ways, keeping F2, F3 only. We'll see that using F2, F3 only, we can give it like this, then we'll multiply it with F4. After that there are 2 ways of selecting this. we can either select this one like this, or we can select this one like this. In either case, F5 multiplying it will add a 1000 part to this. So whatever I do here, F3 itself is taking 25 into 3 by 16 multiplications. That's already greater than 1000. And here F5 multiplication I will be having to do it twice. In whichever parenthesization I select, there are two options here. Whichever I select, this F5 multiplication I have to do it twice. So anyway, that will be way greater than 2204 already. So we don't even need to multiply and check. So these two options are also not right. So B is anyway not answer. Not the answer. We have a better one, A. Option C, F3, F4 only. For this, actually there are three ways of applying the parenthesization. We'll try all one by one. One is F3, F4, and then we multiply F2 to this, and then we multiply F1 to that, and then we multiply F5. Let's try that one. F3, F4 will take 3 by 16 by 1 scalar multiplications. Adding F2 will add 25 by 3 by 1. Adding F1 will do 2 by 25 by 1, and multiplying F5 will get 2 by 1 by 1000. On adding this, we will see that the total here is 2173. This is less than the previous minimum we got of 2200 something. So this is the new minimum, meaning A and B options are definitely wrong. It could be C. We'll try the other two options also and see if we are getting a smaller one. Other two ways of applying parenthesization for this option. The other two ways are, we set F3, F4 initially, and then we can multiply F2 and then F5 and then F1, or F3, F4 and then F5, after that F2, after that F1. But in these two cases, you can see that F5 itself will add a scalar multiplication value of at least 1000 multiplied by something from the other matrices, and F5 is getting multiplied twice here, one here and one here. In this option also once with this, and at the end with this. So anyway, this will be greater than 2173. Here this 1000 part was only coming once, multiplied by 2, and then all those were smaller values. So these we don't even need to calculate. It will be anyway greater than 2173. So for C, the minimum is 2173. We'll look at option D here now. D says F1, F2 and F3, F4 only. So for doing this, there are two ways of applying the brackets. One is F1, F2, F3, F4. We multiply these two, and at the end we multiply F5. On doing that, we get the following here. The answer is 2204. That is still greater than 2173 we got previously. So this is not the minimum. The other way is doing it like this. But here also again F5 is coming twice. We multiply this and then we multiply F5 here. That will add 1000 multiplied by something. Also to this also we will be multiplying this F5 part, right? That will again add 1000 multiplied by something. So this will also be greater than this. We don't need to calculate. So the minimum we got is 2173 from option C. So option C is the right answer. Consider the following parse tree for the expression A hash B dollar C dollar D hash E hash F involving two binary operators hash and dollar. Which of the following options is correct for the parse tree? So for that expression, we have been given this particular parse tree, and they are asking us about the precedence of these operators hash and dollar, and also their associativity. So based on the parse tree, I will assign parentheses in the expression here. So initially we are calculating B dollar C, and then we are doing it dollar with D, and then we are doing E hash F. After that, we are taking the hash of this part and this part. And at the end, we are taking hash of A. So if you take a look at this, you will see that we are calculating the dollar part first before the hash part. We had A hash B here and B dollar C. We are doing B dollar C before this. So clearly, the precedence of dollar is higher than hash. And also if you take a look here, we have B dollar C dollar D. We are calculating the left part before C dollar D. So dollar is left associative here clearly. And in this expression, if you see, we have a hash, this part hash e hash f, and then we are calculating first this part hash this part, and after that a hash this part. So clearly hash is right associative here. So hash is right associative, dollar is left associative, and dollar has higher precedence. So this is the correct option. Consider the following solution to the producer-consumer synchronization problem. The shared buffer size is n. 3 semaphores empty, full and mutex are defined with respective initial values of 0, n and 1. Empty denotes the number of available slots in the buffer and for the consumer to read from. Full denotes the number of available slots in the buffer for the producer to write to. The placeholder variables denoted by P, Q, R and S in the code below can be assigned either empty or full. The valid semaphore operations are wait and signal. Which of the following assignments to P, Q, R, S will give the correct solution? So in the question, so this is a question from process synchronization topic from operating systems. We are given this producer consumer problem. This is the producer code and this is the consumer code. We need to ensure proper process synchronization such that the producer, once it has something, it will keep on adding to the buffer, and whenever something is there in the buffer, the consumer should read from the buffer. So if the buffer is full, the producer should not be able to add any more to the buffer. Similarly, if the buffer is empty, the consumer can't consume anything from the buffer. So let's take a look at these semaphores and see what they mean. It is saying that full denotes the number of available slots in the buffer. Full is denoting the number of available slots in the buffer. So initially full is assigned to 1, meaning initially there are n slots available in the buffer. So you should note that initially there are n slots available in the buffer. It's not that n slots are completely filled up. So if n slots are available in the buffer and total number of slots are n, which means there is nothing in the buffer currently, n slots are available. So there is nothing for consumer to consume from, and producer can write, that is fine. So initially this wait P, so one more thing, wait, when we apply wait we will be reducing the value here, and when we do signal we will be increasing the value of that semaphore. You can refer to the semaphore section in the video lectures and see what exactly wait and signal mean. So initially producer should be able to proceed without any issues, but consumer should be blocked before full is assigned to n, and meaning that there are n slots available in the buffer, so there is nothing currently. So this wait of R should be blocked. Now this will be blocked if R is full. It will be wait applied on n, that will proceed fine without any issues. So that is not correct. If it is R is empty, meaning that this will be blocked here. Wait when applied of 0, this will be blocked here unless someone increases the value of empty, only then it can proceed. So R will be empty. Similarly for producer we are applying wait of P, and this should go fine initially. So when we are applying wait of P, if P is empty, wait of empty will come and it will be blocked. So producer won't be able to proceed further in the code. That is wrong. We have n slots available. So P should be full instead of empty. So, and after this part, in this part we have acquired the logs, and then we are adding one item to the buffer. When we are adding one item to the buffer, we need to indicate that consumer can now start consuming. That means the value of whatever is R, that should change. Initially it was 0, it should change to 1. So whatever is R should be same as Q, meaning Q will be empty. Similarly, when we are signaling S, that means we have already consumed something. We need to free up one slot. After that wait can run. So whatever is P should be S here. So S will be full. So this is the valid assignments. Looking at options, P full, Q is empty, R is empty, S is full. Option C is the right answer here.
This question is based upon mathematical logic. We have been given a first order logic sentence like this, in which we have if there exists quantifier put upon the variables s, t and u, while a for all quantifier put upon the remaining variables v, w, x and y. Now these are the predicate symbols, not function symbols, and it has a model with a universe containing 7 elements. So these are those 7 elements. And what do we mean by model? Model is basically a domain for which this predicate will be true. For example, let us assume that predicate would have been something like the sum of all these variables s, t, u, v, w, x and y. Let us say that has to be greater than or equal to 100. Now if we set the values of these there exist type of variables s, t and u to be, let us say 20, 50 and 40. Now as we can see that the sum of these three values itself has become 110, which is greater than 100. So now if we substitute any non-zero value or greater than equal to value of the remaining variables, then we will find out that the predicate is always getting satisfied. So it basically means that for these three variables, if we fix some value, then for any value of the remaining variables, our domain or our model will be satisfied. And it is also possible that we put this s value itself to be 200, or we put this s and t together to be 50 and 50. So basically we can form a model of size 3 or less than 3. That is what they mean by this. If the result totally depends upon this there exists type of variables and not upon these remaining variables. Hence we form a model of size 3 or less than 3 to satisfy this predicate equation. So the correct answer will be option A.
Let G be a simple undirected graph. Let TD be a depth first search tree of G. Let TB be a breadth first search tree of G. Two statements are given. One, no edge in G is a cross edge with respect to TD. Cross edge in G is between two nodes, neither of which is an ancestor of the other in TD. 2. For every edge uv of G, if u is at depth I and v is at depth j in TB, then distance between I and j, or modulus of I minus j equal to 1. Which of the above statements must necessarily be true? So this is a question from data structures, particularly graphs. We have been given, say, sample graph G, suppose, and they are asking, suppose we are constructing a BFS search tree and DFS search tree, and these two statements are given. They are asking which of these pertaining to these DFS search tree and BFS search tree are necessarily true. So let's take some sample graph. Let us say that this graph given here is G. Now I will try constructing the depth first search tree of this. Let us say we start from this node and we'll be going depth first here. So from this node I'll be going to this node here. This will have these two children, so I can traverse to one of these. Suppose we go here. This has this again as the child here, so we can go here. This has only these two childs, but we have already covered these two here. So there is no more places to go from here, so we'll traverse back to the root and then we'll go to the next child, that is this one. This has two children, these two. We can go to one of these, say this, and let us say we can go here. So this is the DFS tree here. In red dotted lines I have marked the edges in G which are not there in this DFS tree. So in the question they are asking is, they are saying no edge in G is a cross edge with respect to TD. So let's take a look at this edge. It's between this and this, and this node is an ancestor of this node, so it is not a cross edge. Similarly for this node as well, this edge as well, this node is an ancestor of this node, so this is also not a cross edge. Similarly here as well we have this edge, this node is a parent of this node, so this is also not a cross edge. So in this example we have chosen there are no cross edge, but we can't use it to say that this will always be true. But one property of constructing a DFS tree is that suppose this is actually a cross node. Imagine this was a cross node in G, but when we are constructing the graph, we'll at some point in DFS tree we'll reach one of these nodes and then we will see this edge is there, so this edge will definitely be traversed in some way. So there is no way we can have a cross edge in an undirected graph. You can try out more examples and see that a cross edge will never happen. So 1 is true. Let us look at statement 2. Here we are constructing a BFS tree. The same thing we follow for this graph. We start with this node. Let us say this is a root node. It has these 3 children. So in BFS we will be adding these 3 first at depth 1. Then we look at depth 2 nodes. For this one there is this. We add that here. For this node there's only this node, but we have already added that. There is nothing more to add. And coming to this node we have these 2 as children. So that's also at depth 2. And clearly you can see that this node and this node is at depth 1 here. And there is an edge in graph G, this one, which is not in this. But I and j is 1 in this example. The difference is 0. It is not equal to 1. So this statement is false. So the answer is A, 1 only. And one more thing. They have given that it was an undirected graph. If it was a directed graph like this, and if we were constructing the DFS tree, then from here we would have gone here. But this is a directed node. We can't go to this node directly from this node. So we would have come back and then added this node later. And this edge is there in G, it is not there here, and neither of these nodes are ancestors of each other in this tree. So this is actually a cross edge. So for statement 1, cross edges can happen in directed graphs, but in the question they have given undirected graphs. So A only is the answer. This is a C programming question. Consider the following C code. Assume that unsigned long int type length is 64 bits. Unsigned long fun. This is a program given, and they are asking the value returned when we call fun with input 2 power 40 is dash. So we are using unsigned long int. Its length is 64 bits. So numbers up to 2 power 64, integers up to 2 power 64, it can store without any issues. Throughout we are using unsigned long int, so we can confirm that there is no overflow here. Now we'll take a look at what's happening here. We are calling the function with 2 power 40. So n is 2 power 40 here. Ij and sum is initialized to 0. And in the first loop we are assigning I equal to n. So I becomes 2 power 40. I is greater than 1, that is true. And then we are dividing I by 2 in each step. So initially I is 2 power 40. We'll be doing j plus plus here. Then I will be divided by 2. It becomes 2 power 39. So j plus plus is done. Again it goes on until we reach 2 power 1. Again we do j plus plus. Then divided by 2 will be 1 or 2 power 0. This condition will be false now. So this won't happen. And we'll exit the for loop here. So j plus plus happens from 2 power 40 till 2 power 1. That is 40 times. So j is 40 here. Now we'll come to the second for loop. Here it is running till j is greater than 1. And after every iteration we'll be dividing j by 2. So initially j is 40. From this loop we got 40. And we'll be doing sum plus plus. Again we'll divide it by 2, it becomes 20, we do the same, 10, 5, 2, we do the same, divided by 2 we'll get 1. And when it is 1 the condition will be false and we'll exit the loop. So this happens 5 times. So sum becomes 5. So B is the right answer here. This is a question from disk scheduling algorithms part from operating systems. So the question text is very large, so I have compressed it and written the summary here. To read the full text, please refer to some question papers. So I'll tell you what the question is. They have given us that there is a storage disk with 4 platters numbered 0 to 3, 200 cylinders numbered 0 to 99, 256 sectors per track numbered from 0 to 255, and total 6 disk requests of these form, in which the address mean the first one is the sector, the second one is the cylinder, and the third one is the platter. Initially the head is at sector 100, cylinder 180, moving towards higher cylinder numbers. And they are asking what's the average power dissipation provided that the power needed to move across 100 cylinders is 20 milliwatt. For reversing direction of the head movement is 15 milliwatt. Rotational latency or switching between platters doesn't take anything, we can ignore that. They are asking the total power for shortest seek time first disk scheduling algorithms. So given these disk requests and provided that the head is at cylinder 80, sector 100, moving towards higher cylinder numbers, they are asking we are following shortest seek time first disk scheduling algorithm, what is the total power dissipated. So for disk what we have here is that there will be multiple cylinders and each cylinder will have something called platters. and within each platter there will be multiple concentric circles called tracks, and within tracks there will be each section called sector. You can refer to the disk scheduling part in the video lectures to understand all this first. So in the question they haven't given any information about tracks here, but if you look at the power dissipation table, we will see that we need power only for moving between cylinders and for reversing the head direction. We don't need any power for switching between tracks, switching between platters, and within track moving between sectors and all that. So we don't need any power for that, so we don't need to worry about all that. We just need to worry about moving between cylinders and then reversing the direction. So that effectively means that the information about the sector number and the platter number, all that is useless in this question. We only need to look at the cylinder numbers in the question. So we will write down the cylinders numbers like this. So initially the head is at cylinder 80, and these are the 6 cylinder numbers which I have copied from here. All these ones I have copied like that. So these are the cylinder numbers which we need to move, and initially we are at 80, and we are using shortest seek time first algorithm. So from 80 for shortest seek time first, 80 to 86 will take 6 cylinders, 86 to 80 to 70 will take 8 cylinders, so we'll move first to 86. And from 86, if you look from up to 116, it is what, around 30 movement. 86 to 72 is smaller, so we'll move to 72 first. From here we'll move to 116 following the same algorithm, then to 134, and from 134 we'll come to 20 and then to 16. So the total cylinders moved with this movement is, initially we have 6, 14, 44, then here 18, then from 34 to 16 it will be 118. So the total number of cylinders we have covered here is the sum of all these, which is 200. And in the chart it was given that for moving across 100 cylinders we needed 20 milliwatt power. So moving across 200 cylinders we will need 20 by 100 into 20, that is 40 milliwatt. And also there is power associated with changing the direction of the head. So here there is one direction change, we are moving to the right, then we come to the left. Again here there is one additional direction change, here also there is one direction change. There are 3 times we are changing direction, and power associated with each direction change is 15 milliwatt, so the total is 45. So the total for both of these is 40 plus 45, the answer is 85. Consider the unsigned 8-bit fixed point binary representation below, where the position of the binary point is between B3 and B2. Assume B7 is the most significant bit. Some of the decimal numbers listed below cannot be represented exactly in the above representation. Which of the below statements is true? So in the question they have given us fixed point binary representation as this one, B7 to B3 dot P2 to B0. This is a question from number systems in digital logic design. You can refer to the video lectures for number systems to understand about the different ways of representing decimal numbers in binary form. So in this question they have asked about fixed point binary representation. So in fixed point binary representation, B7 to B3 dot B2 to B0, what it means is that B3 will be 2 power 0, B4 will be 2 power 1, etc. up to B7 will be 2 power 4, and B2 after the decimal will be 2 power minus 1, this is 2 power minus 2, and this is 2 power minus 3. These are the weights associated with each of these bits. So this means that for the part before the decimal, this will be the part before the decimal point in that decimal representation. So this with this part we can represent all the numbers from 0 up to 31. How we got that is, this is 2 power 4 plus 2 power 3 plus 2 power 2 plus 2 power 1 plus 2 power 0. When we assign 1 to all of these, that will be 31 in decimal. So this part can represent all the numbers from 0 to 31. That is the part before decimal. Now coming to the part after decimal, the weight of this is 2 power minus 1, that is 1 by 2. The weight of this is 2 power minus 2, that is 1 by 4. The weight of this is 2 power minus 3, that is 1 by 8. So 1 by 8 is the smallest precision we can get for the part after decimal. Meaning we can, using this part after decimal, we can represent all the numbers like this, 0.000, 0.125, 0.250, etc. up to 0.875. Since the precision is 1 by 8, it only grows from 0, it can only grow by multiples of 1 by 8. And these are the associated representation we should have to get this decimal part. So now let's take a look at the options. For the part before the decimal point, we can have 0 to 31. So this is possible, this is possible, this is possible, and this is also possible. Now we need to look at the part after decimal. 0.500 is a multiple of 0.125. This is there here. So 1 is fine. 0.875 is also fine. It's a multiple of 0.125. 0.100. Now that is not possible. We have to represent either 0.125 or 0.000. 0.100 is not possible with only 3 bits after decimal. So this is not correct. This is also not correct. We can't get 0.001. So they are asking which of the below statement is true. Option C is right. Only 3 and 4 cannot be exactly represented. So C is the answer. This is a question on Banker's algorithm for deadlock avoidance coming from operating systems. Now the question text again was very large, so I haven't written the entire thing. I have given the summary only. For reading the entire question text, please refer to the question paper. So the summary is this: we have been given 3 types of resources, E, F and G, and there are 4 processes currently running, P0, P1, P2, P3. This is the matrix for resource allocation, current allocation, which means that P0 has been allocated 1 resource currently of type E and 0 resource of type F, 1 resource of type G. P2 has been assigned 3 resources of type G, etc. This is the current allocation, and this is the maximum request. So P0 at any time will request up to maximum 4 resources of type E. P2 can request a maximum of 3 resources of type F. This is the total request that will come. And currently after allocation we have 3 instances of E and 3 instances of F available. From a deadlock perspective, deadlock avoidance perspective, which of the below are true? A, the system is in safe state. B, the system is not safe, but it would be safe if 1 more instance of E is available. The system is not safe, but would be safe if 1 more instance of F is available. D says 1 more instance of G is available. So let's take a look at how to solve this. Now we know that this has been allocated currently, and this is the maximum request which can happen. So we will find out how many requests it can request, how many resources it can request in the future. That is nothing but maximum resource request minus currently allocated ones. So that matrix I have drawn here. Let's take a look at one. P0 currently has 1. P0 of type E. P0 can request a maximum of 4 of type E. It currently has 1, meaning in the future it can request up to 3 resources. In the same way I have filled the entire chart. So a column here means P2 now can request up to 3 resources of type F additionally. We have 3 resources of type E available, 3 resources of type F available, and 0 resources of type G available. Now let us see which all we can satisfy currently. We have 3 and 3 available. Let's look at P0. P0 can request up to 3 of E, up to 3 of F, and 0 of G, which is less than what is currently we are having. So we can satisfy P0 here. So let us say P0 is requesting these 2, and P0 runs. After P0 running, it will release what it currently has as well. So we had we had 3, 3 and 0 available. After P0 runs, it will be releasing what it currently has, which is 1, 0 and 1. The total is 4, 3 and 1. Now we have 4 resources of E, 3 resources of F and 1 resource of type G. We can clearly satisfy this one as well. This only needs 3 resources of type F, which we already have. So let us say we allocate the resource to P2. P2 runs and it will release 1, 0, 3 of these types. After P2 runs and releases its resources, we will have 5, 3 and 4 resources of each type. Now P1 can be easily satisfied. Let us say we assign resources to P1. After P1 runs, it will release 1, 1 and 2 respectively. So now we will have 6, 4 and 6 resources of each type. Clearly P3 can also be run. So P3 will run, it will also release, meaning the system is in safe state. There is no deadlock. Consider the following 4 relational schemas. For each schema, all non-trivial functional dependencies are listed. The underlined attributes are the respective primary keys. And then they are given us 4 schemas, and they are asking which of the schemas above is in 3NF but not BCNF. So this is a question from functional dependencies part in DBMS. We have been given 4 schemas here, and the associated primary key and the functional dependencies in each of these have also been given. And they are asking which of these is in 3NF but not BCNF. So let's go through each one by one. So before that, for a schema to be in 2NF, it should satisfy this property such that none of the functional dependencies are of the form partial key to a non-key attribute. This is the condition for 2NF. The condition for 3NF is that none of the functional dependencies should be of the form from a non-key attribute to a non-key attribute. For BCNF, all functional dependencies should be of the form super key to something. You can refer the video lectures for functional dependencies and the normal forms to understand this part. Now let's go through each of these one by one. The first one is roll number to courses. Here roll number is the primary key. So it is of the form super key to something else. So this satisfies the BCNF property. There's only one functional dependency. So this is in BCNF. Let's look at schema 2. The first one is roll number, comma, course ID to email. Roll number, comma, course ID is the primary key here. So this satisfies the BCNF property. The second one is email to roll number. So email is not a key attribute. The key attributes are roll number and course ID here. They have given us the primary key is this. So email is a non-key attribute to a key attribute. So clearly this doesn't satisfy BCNF format, but it doesn't violate 3NF as well. For 3NF, it is violated only if there is a functional dependency of the form non-key attribute to a non-key attribute, but it's a non-key attribute to a key attribute. So this doesn't violate BCNF. It doesn't violate 2NF as well. Email is not partial key. So this is in BCN. This is in 3NF, but not BCNF. Now let's look at schema 3. The first one is roll number, comma, course ID to marks, comma, grades. So this is of the form super key to something else. So this is BCNF. The second one is marks to grade. So marks is not a key attribute. Key attributes are roll number and course ID here. Marks is not a key attribute. Grade is also not a key attribute. So it is non-key to non-key. This violates BCNF. This violates 3NF, sorry. It doesn't violate 2NF. There is no functional dependency of the form partial key to a non-key attribute. So this is in 2NF but not BCNF. Schema 4, roll number, course ID to credit. This is super key to something else. This satisfies BCNF. Course ID to credit. Course ID is a key attribute. So course ID to credit means partial key to credit is not a key attribute. So partial key to non-key attribute. So this violates 2NF as well. So schema 4 is in 1NF but not 2NF. So the question was which of the above is in 3NF but not BCNF. The answer is 2. Given a language L, define Li as follows. L0 equals epsilon, Li equals Li minus 1 dot L for all I greater than 0. The order of the language is defined as the smallest k such that Lk equals Lk plus 1. Consider the language L1 over alphabet 0 accepted by the following automaton. The order of L1 is dash. So this is a question from theory of computation. Here we have given us this particular finite automata for the language L1, and they are asking us what the order of L1 is based on the definition here. We'll come to that now. First let us find out what L1 is. So this is the starting state and that is an accepting state. So clearly epsilon is accepted. This is a language over alphabet 0 only. The first input, let us say it is 0. So 0 will also be accepted. We'll add it here. After that we need to add 0 2 times in order to go to an accepting state. So basically this is the language. What the language shows us is the strings of all zeros of length 0, 1, 3, 5, 7, etc. So this is the language. Now let us try to find out what the order of this language is. Just find out L0. L0 is epsilon, which is given here clearly. L1 is nothing but the language. So L1 raised to 1 is the set of all strings of zeros of length 0, 1, 3, 5, 7, etc. This is the language itself. Now, order of language defined as k is such that Lk equals Lk plus 1, meaning we need to take in progressive steps L0, L1, L2, etc., which is nothing but whatever language we got, concatenating it with L again. Until that, we need to satisfy this property such that after a point, even if we keep on concatenating the language, we won't be adding any more elements to the language. We will keep on getting the same language. So we need to find out the smallest case such that after that point, if we concatenate any more else, we'll be getting the same language only. That is order. So L0 is epsilon, L1 is all strings of zeros of length 0, 1, 3, 5, 7, etc. So these two are not equal. Now let us try to find out L1 square. So L1 square will be L11 concatenated with L11. This is nothing but L1 concatenated with L1. Now L1 has strings of length 0, 1, 3, 5, etc. L1 again has the same. Now we need to concatenate it. For concatenating, we can choose any string from this one and any string from this one, and then we concatenate it. So let's start concatenating 0 with all strings of this language. 0 concatenated with 0. So a string of zeros of length 0 is nothing but epsilon. So this means epsilon concatenated with epsilon. This will give epsilon only. Now epsilon means a string of length 0. So this gives 0. Similarly, a string of length 0 concatenated with string of length 1 will give 1 only. We'll keep on going like this. We will get 1, 3, 5, etc. Now let's take the second string from this language, that is a string of length 1. We need to concatenate that with a string of length 0. When we do that, we'll get 1 here. When we concatenate this with string of length 1, we'll be getting, so this string of length 1 is nothing but 0. This is string of length 1 is nothing but 0. 0 concatenate 0 will be 0, 0. Now we got a new string of length 2, which was not there in the original language. Similarly, if we do 1 concatenated with 3, we will be getting 4. Similarly, we will be getting 4, 6, etc. On taking the next string, that is string of length 3, concatenating that with string of length 0, 1, 3, 5, etc., we will be getting 3, 4, 6, etc. So this we already had. We don't need to do any more. We have gotten all the strings in 0 star. That is, we got the string of length 0, 1, 2, 3, 4, 5, 6. This will keep on continuing like that. Basically, we have got all the strings in the language. That is, L12 is 0 star. Now, if we concatenate any more languages from here, we will be getting some string belonging to 0 star only, because 0 star is covering every strings which can be produced with this alphabet 0. And if we concatenate any more languages, we will be getting something in 0 star only. So L1 cube will be 0 star only. So L12 and L13 is the same. So, but L11 and L12 were not the same. So k equals to 2. This was the smallest case, as that Lk equals Lk plus 1. So the answer is 2. This is a question from computer networks regarding carrier sense based medium access protocol. Now the question text was very lengthy. I have written down the summary here. You can refer to the question paper to see the exact text. So what they were saying in the question is that multiple nodes are connected by a shared broadcast medium. Nodes follow carrier sense based medium access protocol. Nodes do carrier sensing for 5 time units. So how it follows is, it will, every node, when it has a packet to transmit, it will do carrier sensing for 5 time units. And if there are no transmissions detected in this 5 time units, they will start transmitting the packet. And if they detect any transmission, they will wait for the transmission to finish. And then they will do carrier sensing for 5 time units again, and if no collision is detected, that node will start transmitting. So that's how it works. Once a transmission is started, and no collision detection is performed. So after starting a transmission, if some collision happen, the node doesn't care, it will keep on transmitting. All transmissions last for 20 units of time. Signal speed is 10 meters per time unit. Now in the question they are given a model where two nodes P and Q are located d meters apart, and P starts transmitting at time t equal to 0, and Q receives a packet to transmit at time t equal to 0. So it will start its carrier sensing phase at t equal to 0. The minimum distance d that allows Q to avoid collision is. Now this is the model they have given in the question. At time t equal to 0, P is starting its transmission, and here Q will start collision detection. Now Q will perform collision detection for 5 time units, and after 5 time units, if there is no collision happening, Q will start its transmitting at 5 after 5 time units. Now we'll see that all transmission will last 20 units of time. So this will keep on transmission will happen from t equal to 0 to t equal to 20. P will keep on transmitting. Now after that it will reach Q. Now if Q starts transmitting at 5, definitely 5 falls between t0 and 20. So if Q starts transmitting at 5, it will result in a collision somewhere in between. Now before 5 time units are over, this signal should reach Q. Only then Q will be able to detect it. Now if the signal doesn't reach Q before 5 time units, Q will also start transmitting here, and that will result in a collision. Now we know that signal speed is 10 meters per time unit. So it will travel 10 meters in 1 time unit. So in 5 time units, it will travel into 10, that is 50 meters. So if the distance is less than or equal to 50, the signal will reach Q before 5 time units, and Q will detect a collision, and there won't be any collision happening. Q will detect a transmission and there won't be any collision happening, since once a transmission is detected, Q won't be sending again. But if the distance is more than 50 meters, the signal won't reach Q before 5 time units. So Q won't know P is transmitting, and Q will start transmitting, and it will result in a collision. So the answer is 50 meters. A lexical analyzer uses the following patterns to recognize 3 tokens T1, T2, T3 over the alphabet A, B, C. These are the 3 lexical analyzers used here. Note that X question mark means 0 or 1 occurrence of the symbol X. Note that the analyzer outputs the token that matches the longest possible prefix. If the string BBAACABC is processed by the analyzer, which one of the following is the sequence of token it outputs? So this is a question from compiler design token matching section. We have been given this string BBAACABC, and we can match this string to any one of these tokens, and they are asking if for this string what will be the tokens outputted. Now let's try to go through it one by one. The important point to note here is that it matches the longest possible prefix. Now let's take a look at T1. This is A question mark B or C star A, which means 0 or 1 occurrence of A, then B or C any number of times, and then ending with A. Now the first one is not A, so from 0 or 1 occurrence of A, we will choose 0 occurrence of A. Then B or C star, B, so we can match up to here, and then ending with A. So BBA will match token T1. Now let us see if T2 will match. It says 0 or 1 occurrence of B. We will take one B, then it will be A or C, but the next one is B, so T2 can't be matched. Let's take T3, 0 or 1 occurrence of C. The starting one is not C, so it will be 0 occurrence of C. Then B or A star, B, A. We can match up to here, B, A using this part, and ending with C. So C, meaning this is T3. So T1 can match up to here, T3 can match up to here, and it clearly says it matches the longest possible prefix. So Up to here it will be matched with 3, 3. And the rest we have ABC. This again we will go through these one by one. For T1, if we try, we can take one occurrence of A since it starts with A. Then it is B or C. We can take one B and one C. And then it will end with A. But we don't have any more A here. So T1 can't be matched to this. Let's take a look at T2. 0 or 1 occurrence of B. There is no B, so that will be 0. Then A or C star, which there is one A here. The next one is B, so that needs to be stopped here, ending with B, that we can match here. So T2 will be matched up to here. Now let us try T3. 0 or 1 occurrence of C. There is no C here, so that is 0. Then B or A star. A, B we can match up to here. Then C ends with C. So T3 will match A, B, C completely. And again it will take the longest possible prefix here. So T3, T3 is the answer. This is a question from probabilities in engineering mathematics. So the question text was very large. I have written down the summaries here. What they say is H denotes high, M denotes medium, L denotes low, G stands for Guwahati and D stands for Delhi. And we have been given this table which gives the conditional probabilities for Delhi's temperature given Guwahati's temperature. So for example, if I take this cell, it will give the probability that Delhi's temperature is high given Guwahati's temperature is high. HD denotes high for Delhi, MD denotes medium for Delhi, LD low Delhi. Similarly, so P of HD given HG means probability that Delhi's temperature is high given Guwahati's temperature is high. Now that information we have been given in this table, and it is known that probability that Guwahati's temperature is high is 0.2, P of Mg meaning Guwahati's temperature is medium is 0.5, and P of Lg meaning Guwahati's temperature is low is 0.3. Then the probability that Guwahati has high temperature given that Delhi has high temperature is. So what they want is to find out P of high of Guwahati given high of Delhi. But what we have is P of high of Delhi given high of Guwahati, and the values for P of high of Guwahati, medium and low of Guwahati. So we'll see how we can solve this. Now P of high of Guwahati given high of Delhi is P of high of Guwahati and high of Delhi divided by P of high of Delhi. Now this will be P of high of Delhi given that high of Guwahati into probability of high of Delhi by P of high of Delhi. This is Bayes' theorem. Now here this value we already have. We have that from here, P of HD given HG. P of HG is also given here, but P of HD, this we don't know. Probability that Delhi's temperature is high, this we need to calculate. Now probability that Delhi's temperature is high, there can be three options: Delhi's temperature is high and Guwahati's temperature is high, or Delhi's temperature is high and Guwahati's temperature is medium, or Delhi's temperature is high and Guwahati's temperature is low. So probability that Delhi's temperature is high will be the sum of these. Now probability that Delhi's temperature is high and Guwahati's temperature is high can be rewritten as P of HD given HG into P of HG. This is just rewriting what I am given here. P of HG and HD is P of HG given HD into P of HD. So just rewriting it in this format, we get this particular formula. Now the good thing about that is all of these values we clearly know. These three values I can directly take from the table: P of HD given HG, HD given Mg and HD given Lg. That I can take directly from the table. And probability of higher Guwahati, medium of Guwahati and low of Guwahati, that's also given in the question here. So now I can substitute the values there and I can calculate it. It will be 0.4 into 0.2 plus 0.1 into 0.5 plus 0.01 into 0.3, that is 0.133. Now this is the probability that Delhi's temperature is high. Now I need to substitute this value here so that I can get probability that Guwahati's temperature is high given Delhi's temperature is high. Now I will substitute the values here. This we know from the table. This also we know given in the question. This is the calculated value. The answer is 0.60. The probability that Guwahati's temperature is high given Delhi's temperature is high is 0.60. Consider the following program written in pseudocode. Assume that x and y are integers and they have given us this pseudocode. The number of times print statement is executed by the call count 1024, 1024 is that. So this is a question from programming. They have given us this particular pseudocode and you can see this print statement here. They are asking how many times this print statement is executed. So let's take a look at this function. Initially we are calling it 1024 by 1024, that is 1024 by 1024. So if you take a look here, if y equals 1, this entire block is for y not equal to 1. If y equals to 1, we will exit this function immediately without printing anything. So the exit condition for this is that y becomes 1. Now if y is not equal to 1 and if x is not equal to 1, then we will be printing something and then we will call the function again. If y is not 1 and x is 1, here we won't be printing anything but we will call this function again. So let's take a look how it proceeds. So initially we called it 1024 by 1024. X is not 1, y is not 1, so we will print something here and then we will call this function again with x by 2. So x by 2 is 512, so we will call again with same x by 2 and y. So we will call it with 512, 1024. Again, x is not 1, y is not 1, we will print something. This proceeds up to here. X becomes 2 power 1, we will call it 2 power 1, 1024. Again, this is satisfied. We will call count again. Now, when we divide this x by 2, it becomes 1. So, when we call it with 1, 1024, y is not 1, that is true, but x is not 1, that is false. So, we won't be entering this block. Instead, we will go to this block. In that block, what we will do is we won't be printing anything. We will decrement y by 1 and then we will call count with 1024, y. That is, we will decrement this by 1. And we will call again with 1024, 1023. So if you take a look here, in all these calls, x changes from 2 power 0, 1, 2 power 2 up to 2 power 10. Only from 2 power 10 to 2 power 1 we are printing something. In this block we are printing nothing. So here to here, actually there is 10 function called 2 power 1, 2 power 2, 3, 4 up to 10. So like this, here we will be printing 10 times. In this function call we are not printing anything, and then this will call again x with 1024, y with 1023. This will also proceed in the same fashion. X will keep on changing from 2 power 10 to 2 power 1 and then 2 power 0 where we won't be printing anything. From here to here we will be printing 10 times. Y will be 1023 here. This will call again with 1024, 1022. Again it will proceed in the same fashion. So if you see, for every y value we will be executing the print statement 10 times, and y changes from 1024, we will be printing 10 times depending on the function calls. Then y changes to 1023, again 10 times, and y changes to 1024, etc. Y will keep on reducing, y will reach 2. We will call 1024, 2. It will also proceed in the same manner. After that, we will call with 1024, 1. At that point, if you see this entire block, we won't enter inside it. We will see that y equal to 1 and then we will exit. So, that is the exit condition getting satisfied there. So, when y changes from 1024 up to 2, we will be printing that print statement 10 times. So y moves from 2 to 1024, meaning there are 1023 values for y, and in each of the one value for y we will be executing the print statement 10 times. So the total number of times the print statement is executed is 1023 by 10, that is 10,230. Consider the following languages. They have given 4 languages here, and they are asking which of the following languages are context free. Now this is a question from theory of computation section for context free languages. We are given the definition for 4 languages and we need to find out which among these are context free. Let's take a look at the second one first. A, M, B, N, C, P, D, Q, such that M equal to N and P equal to Q. So This is a standard context-free language. Here we need to match the number of A's and B's. Number of A should be equal to number of B and number of C should be equal to number of D. That we can easily do by pushing A's to the stack, and then for each B we need to pop the A's and then the stack should be empty. After that we need to keep on pushing all the C's, and then for each D we see we'll be keeping on popping the C's from the stack, and the stack should be empty at the end. So this is easily a context-free language. Let's look at the third one. Here M equals N equals P. Now here we need to match the number of A's, B's and C. The number of A, B, C all should be equal. Now this is not a context-free language, it's a context-sensitive language. In the stack we can push all the A's, and then for B's we need to either pop the A's or then we can push the B's. But then after that there is no way to match for the C here using only one stack. So this is not a context-free language. You can refer to the video lectures and you can see that it's actually a context-sensitive language. So this is not. Let's look at the third one. Here Mn equals Pq. We need to multiply the number of A's and B's, and then we need to match it to the sum of C's and D's. Multiplication and other arithmetic operations we can't perform using a stack. So this is not a context-free language. Now if you look at the options, 3 and 4 are not context-free, so B looks like the answer. It says 1 and 2, so let us check for 1 if it's a context-free as well. Now in A the case is that M plus P should be equal to N plus Q. We can rewrite it as M minus N equals Q minus P. So let us try to design an algorithm using which we can show that it is context free. Let us say for M's it is A's, right? So we'll be, for whatever A's we are seeing, we'll be pushing all the A's to the stack, and then B's will come. For B, here it is minus N. So what we'll do is we'll keep on popping the A's for each of the B's seen. Now there can be two cases. One is that the number of A's is greater than number of B's. In that case there will be some A's left over in the stack, or the number of A's equal to the number of B's. In that case the stack will be empty, or that the number of B's can be greater than the number of A's. In that case you will keep on popping A's from the stack for each B seen, and then after that there will be a few leftover B's. What we'll do is, if A's are over, we'll keep on pushing the B's to the stack. So the stack will look like one of these three at the end. After that we'll start seeing C's here. For C it is P here, and the formula here is minus P. So what we will do is, if the stack looks like one of these, if there are A's or if the stack is empty, we'll push all the C's which we are seeing there. So the stack will look like 0 or more A's at the bottom and then C's on the top. Or if there are B's in the stack, the meaning is that the number of B's were greater than the number of A's we saw. So if that is the case, then we won't be popping up these B's. Instead we'll be, in that case we will be popping off the B's and then we'll be pushing the C's after the stack is empty. So there are two cases. I'll repeat again. There can be A's or the stack is empty. In that case we won't be pop anything from the stack. We'll just keep on pushing the C's on top of it. Or if it is B's, then we will pop off the B's one by one for each of the C's seen, and after the stack is empty, if there are leftover C's, then we will push the C's to the stack. After that we'll start seeing D. In that case what we will do is we'll pop off D's for C or A, C in the stack. If it is C or A in the stack, we'll pop off that element from the stack for each of the D's seen. There should not be any B's in the stack. So this is the algorithm for proving that this is a context-free language. This is the push-down automata for satisfying this language. You can try it with multiple examples and see that this always works for the given example, and this is the answer. Consider the following problems. L of G denotes the language generated by a grammar G. LM denotes the language accepted by a machine M. And we have been given 4 statements. They are asking which of the following statement is correct. So we are given 4 statements regarding grammars and machines and languages, and they are asking which of these are undecidable actually. This is a question from theory of computation, decidability and undecidability. So we'll go through these statements one by one. First one says that for an unrestricted grammar G and a string W, whether W belongs to G. Now this is membership problem. The grammar given is unrestricted grammar, meaning recursively enumerable languages. The membership problem for recursively enumerable languages is undecidable. So this is undecidable. Second, given a Turing machine, whether L of M is regular. We have been given a Turing machine and then we need to find out from there itself whether the language accepted by the Turing machine is a regular language. There is no algorithm which we can lay out using which we can check whether a Turing machine is accepting a regular language. This is also undecidable actually. Third, given two grammars G1 and G2, whether L of G1 equals to L of G2. Now this is the equality problem for these two grammars. Now they haven't said anything about the type of grammar. If they were regular grammars, then this equality problem would have become decidable, but nothing has been told about the grammar, so we can't assume it's a regular grammar. So if it is not regular for context free or any other languages, this is undecidable. So we'll say that this is undecidable. Fourth one, given an NFA N, whether there is a deterministic PDA P such that N and P accept the same language. Now given an NFA N that accepts a language, whatever language accepted by an NFA is a regular grammar. It's a regular language. Okay. So every regular grammar is also a context free grammar. So meaning that for every context free grammar there will definitely be a push down automata. So if there is an NFA N accepting some language, there will definitely be a deterministic push down automata accepting the same language, which means that this is decidable actually. So the answer is only 1, 2 and 3 are undecidable. Consider the relations R, A, B and S, B, C, where S dot B is a primary key and R dot B is a foreign key referencing S dot B. Consider the query R join sigma B less than 5 of S. Let L or J denote left outer join operation. Assume R and S contain no null values. Which of the following is not equivalent to Q? So this is a question from relational algebra from DBMS. We have been given these 4 relational algebra queries and they are asking which of these is not equivalent to this query. So let us consider that this relation is this and S is this. We will take in 2 sample relations. Now the B values in R is 1, 2 and 8. This has to reference B values in S. 1, 2 and 8 should be here, that is there. And also there is one additional value in S, 5, C. Now let us try taking this. Now this operation is join and this is sigma. So if you don't understand sigma or join operation relational algebra queries, you can refer to the video lectures and get more understanding. So sigma B less than 5 of S will return all the rows such that B is less than 5. It will return these 2 rows, 1A and 2B. And then on performing natural join, it will match those rows having B value equal to the B value in whatever is returned from here. So whichever B values are not matching, it won't be returning those. So natural join of this and B less than 5 of S, that will be these 2 rows. So natural join of this and this will be only 1 and 2 getting matched here. There will be 3 columns in the final matched one. So it will be, there will be B values 1 and 2 here. Now let's consider C operation. R left outer join of sigma B less than 5 of S. Now sigma B less than 5 of S returns the same thing, but when we are doing left outer join instead of natural join, whichever B values in R, every B value in R would be printed in the final answer. But in natural join, only B values in R which matches with whatever is returned here will be printed. So when we take left outer join, we will be getting this particular DB. 1 and 2 will be matched with these 2 rows. For 8 there is nothing matching, so it will be printing null here. So clearly the query C is not equal to the query given in the question. Now you can try out A, B and C and see that it will be returning the same as query Q. So C is the answer. Consider an IP packet of length 4500 bytes that includes a 20 byte IPv4 header and a 40 byte TCP header. The packet is forwarded to an IPv4 router that supports a maximum transmission unit of 600 bytes. Assume that the length of the IP header in all outgoing fragments of this packet is 20 bytes. Assume that the fragmentation offset value stored in the first fragment is 0. The fragmentation offset value stored in the third fragment is dash. So this is a question from computer networks regarding IP fragmentation. So what fragmentation means is that here we have a packet of length 4500 bytes. So each IP datagram has a length of 4500 bytes, but some transmission channel might not be able to send a packet of size this large. So that what the router will do is, it will know that what the channel can accept, the maximum size the channel can accept. Based on that, it will divide this IP packet into smaller packets. So each packet will have a fragment offset associated with the packet to know what is the sequence of the packet in that large packet. Let's say we divide it into 3 packets, so we need to know the order or the sequence in which the packets that can be reassembled later, right? So that is what fragmentation is. You can refer to the video lectures to understand that in detail. And we'll take a look at this question. The IP datagram has a length of 4500 byte. Now 20 byte is IP header. They have given us TCP header as well, but that doesn't matter. From IP perspective, the header is 20 and the data part is 4500 minus 20, that is 4480. This much is the TCP segment length. Now we need to divide this into smaller packets such that each packet's maximum length is 600 byte. Now let us say this packet is 600 byte. So the header itself will be 20 bytes. Each packet also needs its own IP header. So the rest, the data can be at max 580 bytes. But then another property of doing fragmentation is that the length should be a multiple of 8. Why this is? The reason is that fragmentation offset is a 13-bit number in IP header, whereas the total length is a 16-bit number in IP header. So in total length, whatever is the number, that is the number of bytes that packet has, the length in bytes. But whatever is given in fragment offset, we need to multiply it by 8, or we need to apply a scaling factor to make the size correct. To make a 16-bit field of length, we need to compress it to a 13-bit field. So we need to apply a scaling factor of 8 here. So 580 is not a multiple of 8. So the maximum multiple of 8 less than 580 is 576. So the length of the packet would be 576. Adding a header of 20, the total will be 596, which is less than 600. So each packet, each fragment will be having data part of 576 and a header part of 20. Now 576 divided by 8 is 72. Now this is the number that will be stored in fragment offset. So let us see what will happen in the third packet. In the first packet, the fragment offset would be 0, and we are sending 576 byte as data, meaning the second packet will have a fragment offset of 72, denoting that already 576 bytes have been sent. So this will also have 576 byte of data. This will also add a fragment offset of 72, meaning the third one will have a fragment offset of 144. This denotes that a total of 576 plus 576 data has already been sent in previous fragments. 144 is the answer here. Let n be the set of natural numbers. Consider the following sets: P, the set of rational numbers; Q, the set of functions from 0, 1 to n; R, the set of functions from n to 0, 1; S, the set of finite subsets of n. Which of the above sets are countable? Now this is a question from countability theory, from theory of computation. Here we have been given 4 sets and we need to find out which of these are countable and which are uncountable. Now one way of proving that a set is countable is if we can have a one-to-one correspondence to the set of natural numbers. That is, we need to write down each of the elements in the set in some order, and we need to have a correspondence to the set of natural numbers, that is 0, 1, 2, etc. Then we can show that a set is countable. Let's go through these options one by one. P, the set of rational numbers. A set of rational numbers is countable, and you can find the proof in multiple places. This is the basic set we learned while learning countability. There is a one-to-one correspondence to a set of natural numbers. This is clearly countable. 2, the set of functions from 0, 1 to n. Let's take a look at S first, the set of finite subsets of n. Now I will show you how we can prove that this is also a countable set. Now for having an enumeration for the finite subsets of n, let us consider these sets of natural numbers such that the set of natural numbers up to 0, the set of natural numbers from 0 to 1, the set of natural numbers up to 0, 1, 2, the set of natural numbers up to 3, that is 0, 1, 2, 3, etc. We can write down in this format. Now from this we can find out subsets, finite subset. Subsets of 0 are 5 and 0. The subsets of 0, 1 which is not already covered is 1 and 0, 1. The subsets of 0, 1, 2 is which is not already covered is 2, 0, 2, 1, 2, 0, 1, 2, etc. So this keeps on going in this format, and we can have a one-to-one correspondence to the set of natural numbers here. 5 will mark as 0, this will mark as 1, set 1 will mark as 2, 3, 4, 5, 6, 7. In this way we can have an order and we can write down every finite subsets of n in this format. So this is also countable. Now let's take a look at Q, the set of functions from 0, 1 to n. Now let's write down these sets which we obtained here, the set of natural numbers up to some value, up to 0, up to 1, up to 2, etc. And from this we can write down all the functions from 0, 1 to n. If the set is 0, then there is only function from 0, 1 to n, that is 0 is assigned to 0, 1 assigned to 0. If it is 0, 1, then the function which is not already covered is 0 assigned to 0, 1 assigned to 1, 0, 1, 1, 0 or 0, 1, 1, 1. Similarly, from the set 0, 1, 2 also we can write down all the new functions obtained. So this will go in this format, and this we have an ordering and we can write down all the functions in this format. So again this will also have one-to-one correspondent to set of natural numbers. We can mark this as 0, 1, 2, 3, 4, etc. So this set is also countable. Now R is the set of functions from n to 0, 1. Now this is not countable. Here we can't have a one-to-one correspondence to the set of natural numbers. This function is from n to 0, 1. So while assigning values 0, 1 to n itself, that itself becomes an infinite length thing. We can't have a correspondence. We can't finish the first one and then go to the second one. In this way we can't have a ordering. So this is not countable. This is uncountable. So the answer is P, Q and S. Option D. This is a question from dynamic programming in algorithm section. So the question text was very large. I have given the summary of the text here. Let's take a look at the question. Consider the weights and values of items listed below. Note that there is only one unit of each item. So this is a 0, 1 knapsack problem. And what we have to do here is that we need to pick a subset of these items such that the weight is less than or equal to 11 kg and the value is maximized. Now there are two ways of doing this. One, we will have the optimal algorithm which will give the maximum value, that is denoted by V opt. There can also be a greedy algorithm which was given in the question. We can follow that approach. It will give us a value named V greedy. Now the greedy algorithm, what it does is it will sort the items based on their value to weight ratio, and then it will start picking them greedily. That is, it will pick the item having the highest value to weight ratio, and then it will pick the second item having the value to weight ratio. In that order it will keep on going and pick items. So that will give us the V greedy value. Now the question what they are asking is the value of V greedy minus V opt is dash. So clearly V greedy will be greater or equal to V opt, since optimal algorithm will give us the maximum possible value. So let us try the greedy algorithm approach. We need to write the value to weight ratio of each item. So the first one, value is 60, weight is 10. So the value to weight ratio of the first item is 6. Similarly, dividing the value by the weight, we will get that these are the value to weight ratio of each of these items. So the highest value to weight ratio is by item 4. So we will pick that item. We are picking item 2, weight is 2, which is less than 11, and it will add a value of 24. Now the remaining weight is 9. So the second item in this list is item 1, having value to weight ratio of 6. But item 1 has a weight of 10 and we have already added item 4. So the remaining is only 9 kgs available. So we can't add item 1 here. After 1, the next one is item 3, having value to weight ratio of 5. Item 3 has a weight of 4 and it adds a value of 20. We can add that. So these two will be there. The remaining weight is, we already used up 6, the remaining weight is only 5. The next item is 2, but it has a weight of 7, we can't add that. So greedy algorithm will give us these two items having these two values, a value of 44. Now we need to find out what the actual maximum value is. We need to find the optimal algorithm. We need to find the optimal value. Now we need to, the way to solve 0, 1 knapsack is using dynamic programming, but here there is only 4 items and we can try out these without actually writing the DP and the entire table to solve this question. Let us say I am picking item number 1. It has weight of 10, so which is less than 11, so I can use that item. It will add a value of 60. So if I pick item 1, I will get a value of 60. Clearly that is greater than 44. So currently 60 is the maximum value I got. Now let us see if there is any other combination using which I can maximize this value even further. So let us say we have picked item 1. Now can we add any other item to this list? No, because the weight is 10, the remaining weight is only 1 kg. We can't add any more items to that list. All of those have a minimum weight of 2 at least. So item 1, if we pick, that's only item which will be there in our bag. So item 1 will give a value of 60. Now let us try item 2, which has a weight of 7. The remaining weight is 4. So any one of these two items can be picked. If I pick 7 and 2, it will add a value of 28 plus 24, which is less than 60. So that is not the maximum. If I pick 7 and 4, it will be 28 and 20, that is also again less than 60. So if I pick 7, there is no better way to maximize it further than the initial set of just 1. So the only other way of doing this is I can pick item 3 and 4 again. That will be 20 plus 24, that's again less than 60. So optimal maximal value is 60. 60 is the value returned by the optimal algorithm. So in the question they are asking V greedy minus V optimal, that is 60 minus 44. The answer is 16. Consider a matrix P whose eigenvectors are multiples of 1, 4. Which of the following options is correct? P does not have an inverse, P has a repeated eigenvalue, P cannot be diagonalized. They have given us the options. So this is a question from linear algebra. In order to answer this question, you need to know what eigenvectors are, eigenvalues are, and also how to calculate the inverse of a matrix and diagonalization. These concepts you need to know in order to answer this question. So let's go through these statements one by one. The first one says that P does not have an inverse. A matrix P does not have an inverse if and only if the determinant of the matrix is 0. Now if the determinant of a matrix is 0, it will mean that lambda equal to 0 must be an eigenvalue of the matrix. But in the question they have only said that it has a repeated eigenvector. They haven't said anything about eigenvalue, so we can't assume that eigenvalue is 0, which implies that this is not always true. In the question they are asking which of the statements are necessarily true, so we can't say that this is true, so this statement is false. Now let's look at statement 2. P has a repeated eigenvalue. Now let's assume that it has two distinct eigenvalues, lambda 1 and lambda 2. If these two are the eigenvalues, then we can write these two equations. P is a matrix into x1, this is an eigenvector, equal to lambda 1, so first eigenvalue, into x1, same eigenvector. But in the question they have given us that eigenvectors are multiples of 1, 4, so it's a repeating eigenvector. So there's only one eigenvector, so with the same eigenvector we can write that P x1 equal to lambda 2 into x1. Lambda 1 and lambda 2 are the eigenvalues which our assumption is they are distinct, but there's only one eigenvector x1. This is 1, 4. So we can write these two equations. So Px1 and Px1 are same, which means that lambda 1 x1 equal to lambda 2 x2. And from this we can conclude that lambda 1 equal to lambda 2, meaning that if we have repeating eigenvectors, the eigenvalues will also be same. So meaning we have a repeated eigenvalue. So statement 2 is correct. Now let's look at statement 3. P cannot be diagonalized. A matrix P is diagonalizable if there exists a diagonal matrix X and an invertible matrix S such that X equal to S inverse P S. So a matrix is said to be diagonalizable if we can find a diagonal matrix similar to that matrix, and the diagonal matrix X can be written as S inverse PS, where P is the original matrix we have. S inverse will be the matrix obtained by keeping the eigenvectors of P as the column. So we obtain all the eigenvectors and we write them down as columns, and the final matrix we get will be this matrix S. And X will be the diagonal matrix obtained by writing the eigenvalues of P along the diagonals. So for X to exist, this matrix S must be invertible. If it's invertible, then we can write X as S inverse PS. Now let's try to construct this matrix and see if it has an inverse. So S equal to, we need to write the eigenvectors as diagonals. So there's only one eigenvector, it is repeating, so we'll write 1, 4 along the columns. Now clearly this matrix has determinant 0. Determinant of matrix is 4 minus 4, which is 0, which implies that S inverse doesn't exist, which implies that P is not a diagonalizable matrix. So this statement, P cannot be diagonalized, that's also true. So looking at the options, we can say that D is the correct answer. So there's one more point. Since we got a repeated eigenvectors, this matrix is clearly not diagonalizable. But if we had repeated eigenvalue, only if this part is just given, we cannot say that the matrix cannot be diagonalized is true. Repeated eigenvalue doesn't mean that the matrix is not diagonalizable, but repeated eigenvectors means that the matrix is not diagonalizable. The number of possible min heaps containing each value from 1, 2, 3, 4, 5, 6, 7 exactly once is dash. So this is a question from data structures regarding min heaps. A min heap will be a balanced binary tree which satisfies the property that every node will have a value less than or equal to the value of its children. Meaning this node will have a value less than or equal to the value of this and this node. Similarly, this node will have a value less than or equal to the value of these two nodes. So they are asking us, given these 7 values 1 to 7, using them exactly once, if you are constructing a min heap, how many possibilities are there? Now clearly the smallest value has to be the root node, because this node has to be less than these two nodes, this has to be less than these two, this has to be less than the value of these two nodes. So clearly the root node has to be 1. So we will assign 1 to the root node. There are 6 numbers remaining. These 6 numbers we can assign to any of these 6 nodes. So let us try assigning to the left subtree 3 values to the left subtree. The number of ways of selecting 3 out of these 6 values is 6C3, that is 20. So there are 20 ways of choosing 3 values for the left subtree. Now let us see how these, out of these 20 possibilities, how each one can be assigned. So let us say one sample we have chosen is 3, 5, 7. So clearly this node has to have the smallest value among those 3, because this node's value should be less than or equal to these 3. Meaning if we are choosing 3, 5 and 7 for the left subtree, this node value should be 3. Then we have 5 and 7. 5 and 7 can be assigned anyway, 5 here, 7 here, or 7 here and 5 here. That doesn't matter. So meaning that each of these chosen values, there will be 2 factorial additional ways to add to the left subtree. 2 factorial is 2. So for left subtree, we need to choose 3 elements. There is 6C3 ways of doing that, and out of those there will be 2 factorial ways of arranging that greater 2 values in the bottom 2 nodes. Now let us come to the right subtree. We have already taken 1 for the left subtree, that is 3, 5, 7. There is only 3 values remaining, that is 2, 4 and 6. So clearly that value has to be assigned directly here. So there is no addition, there is no further combination part for the right subtree. But these values 2, 4, 6, that can be assigned anyway. So let us check for that. Clearly this should have the smallest value. So this node we will assign 2. Then there are 2 nodes here to which we can assign 4 and 6. Now 4 and 6 we can apply 4 here and 6 here, or 6 here and 4 here. Again there is 2 factorial additional ways to add to the right subtree. So the number of total ways is we need to choose 3, that will be 6C3, and then we have 2 possibilities for the left subtree, that will add a 2 factorial factor, and then there is one additional 2 factorial for the right subtree, that is again 2 factorial. So the total number of ways of arranging to this min heap is 20 by 2 by 2, that is 80. Let G be a graph with 100 factorial vertices, with each vertex labeled by a distinct permutation of the numbers 1, 2 up to 100. There is an edge between vertices u and v. if and only if the label of u can be obtained by swapping two adjacent numbers in the label of v. Let y denote the degree of a vertex in G and z denote the number of connected components in G. Then y plus 10z equal to dash. This is a question from graph theory. Though the question appears to be complex, it's actually a simple question. I'll show you how to do it here. So here we have been given a graph G having 100 factorial vertices. Obviously 100 factorial is a very large number. We can't draw that graph and try to find the answer to this. But we can draw smaller similar graphs and try to find out patterns from it. So I'll try to draw a graph with 2 factorial vertices first. Now 2 factorial is 2. There will be 2 vertices. That will be 1 2 and 2 1. So how can we add an edge between 2 vertices is, there's an edge if and only if the label of u can be obtained by swapping 2 adjacent numbers in the label of v. So let's take any vertex, and if we can swap any 2 adjacent numbers and get the label of a different vertex, there will be an edge between those 2 vertices. So 1 and 2, there is only one swapping which can be performed, that is 2 1. Obviously that is this vertex, so there will be an edge between these 2 vertices. So this is the graph with 2 factorial vertices. The degree of each vertex is 1 here. So y is denoting the degree of each vertex, and the number of connected components is also 1, which is z. This forms one simple connected component. So for this graph, y is 1 and z equal to 1. Now let's try a graph with 3 factorial vertices. 3 factorial is 6. So there will be 6 vertices for this graph, and those will be given as 1 2 3 1 3 2 etc. These are the 6 vertices. Now let's try drawing edges. Let's take the node 1 2 3. There are 2 ways we can swap adjacent elements and form a different label. So we can swap 1 and 2. In that case we will get 2 3 1. That is this node. So we'll form an edge here. Also one more way is we can swap 2 and 3 to get 1 3 2. That is this node. So that is denoted by this edge. So from this node there will be 2 edges. Similarly from each node we can try the same, and we'll see that this is the final graph. So here the degree of each vertex is 2. So y is 2 and z is again 1. This entire thing forms a connected component. So now we can see that patterns are starting to form here. Let us take a look at this full graph now. It has 100 factorial vertices. Now let's take one sample vertex from this graph, that is 1 2 3 4 up to 100. This forms one of the permutations of the numbers from 1 to 100. Now we need to swap 2 adjacent elements from here. From 1 and 2 I can, from up to 1 to 100 I can swap 1 and 2 or 2 and 3 or 3 and 4 up to here 99 or 100 we can swap. So we can do this swapping in 99 ways and obtain a new node. So from this node there will be 99 edges going outside. So the degree of this vertex will be 99. So this follows our pattern. For 2 the y was 1, for 3 y was 2, here it will be 99. That is proven here. Now again these 2 graphs, if you look, this forms one full connected component. Similarly for here also, whatever swapping I do, I can always reach one other permutation in 100 factorial permutation using any number of swaps. So finally the full graph will be one single connected component. You can try out and verify it for yourself. So the number of connected components here will be 1. So z will be 1, y will be 99. So the answer is y plus 10z, that is 99 plus 10 into 1, which is 109. This is a question based on pipelining concept from computer organization. The question text was pretty large, so I have written the summary here. Let's see the question. The instruction pipeline of a RISC processor has the following stages: instruction fetch, instruction decode, operand fetch, perform operation and write back. Instruction fetch, instruction decode, operand fetch, write back all take 1 cycle each. Total there are 100 instructions. In perform operation stage, 40 instructions take 3 cycles each, 35 take 2 cycles each, and 25 instructions take 1 cycle each. Assume no data or control hazard. The number of clocks required for completion of the instruction is dash. So we have been given these operations which we need to perform, and we need to find out what's the total number of cycles which it will take to perform all of these. So let's start with the instruction in which the PO stage take 3 cycles each. So the first stage is instruction fetch, then instruction decode, operand fetch, then perform operation, which will take 3 cycles, and then there is write back. That will take 1 cycle. So total for the first instruction it will take 7 cycles. From the second instruction onwards, we can make use of pipelining concept and reduce cycles per instruction. So instruction fetch I can perform just below this. Instruction decode I can perform here. Operand fetch I can perform here. But in this cycle I can't do perform operation for the second one, because perform operation is taking 3 cycles here. So I can perform operation only after perform operation for instruction 1 is complete, that is here. It will take 3 cycles for perform operation, then it will take write back. So total it was 7 cycles up to here, 3 additional cycles, so it will be 10. Similarly for instruction 3 I can do instruction fetch, instruction decode, operand fetch, etc. anywhere here. But perform operation I can start only after perform operation of instruction 2 is complete. So it will start here, it will take 3 cycles, then write back. So it will be 13 here. So if you see, each instruction is adding 3 additional cycles from the previous one. So first one took 7 cycles. Then there are 39 instructions which take 3 cycles each for perform operation. Each of those will add 3 cycles each. So the total cycles in order to complete for the first 40 instructions is 39 into 3 cycles each plus the initial one taking 7 cycles. So the total is 124. So after the 40th instruction, it will look something like this: 3 PO, then write back. At the end, it will be 124 as seen from here. So it will take 124 cycles to perform 40 instructions of 3 cycles each. Then we will start with the instruction which take 2 cycles for perform operation. For that also, instruction fetch, instruction decode and operand fetch we can write somewhere here. The perform operation will take 2 cycles which I can start only after PO of the 40th instruction. So perform operation and then write back. So up to 40 it was taking 124 cycles. It will take 2 additional cycles here. Similarly for each of the instructions which take 2 cycles for perform operation, it will add 2 additional cycles for each instruction. There are 35 instructions like that which take 2 cycles for, so the total number of cycles added is 35 by 2, which is 70. So to 124 we can add 70, we will get 194. This is the 75th instruction. So up to 75 it will take 194 cycles. These are instructions which take 3 cycles and 2 cycles. Those are complete. Now we just have 25 instructions which take 1 cycle for perform operation stage. We can write those also. After the perform operation of the 75 instruction, I will do perform operation. Now it needs only 1 cycle and write back. So it will add 1 additional cycle. 194 plus 1 is 195. Similarly, each of the next 25 instructions will add 1 cycle. So the total is 25 by 1, 25. So the answer is, here it took 194. The next of the 25 instructions will add 25. Total is 219 is the answer. Consider the minterm list form of a Boolean function f given below. F p q r s equal to sigma m 0, 2, 5, 7, 9, 11 plus d 3, 8, 10, 12, 14. Here m denotes minterm and d denotes don't care term. The number of essential prime implicants of the function f is. So this is a question from K-maps in digital logic design section. If you don't know how to construct K-maps, please refer to the video lectures regarding K-map and learn those first. So here, based on this information, I will construct the K-map here. Here minterms are given as 0, 2, 5, 7, 9, 11. So in the K-map, to those terms I can write 1, which I have given here. And also we have these don't care terms 3, 8, 10, 12 and 14. There I will mark X in those corresponding columns. Now the don't care term can be 0 or 1 here, and now we will try to identify the prime implicants in these such that the don't care term can be 0 or 1. So let's take it these two. These are 1, 1. There's only one don't care term here. Using these two we can form a prime implicant, and this we can't expand to top or bottom, left or right. So this is one prime implicant. Now let's take it these two, 1 and 1. You can see that there's an X on top and there's an X on top. So using these 4 we can construct the prime implicant. To the right side we have 1 here, X here, but we don't have anything here. So we can't expand this further to the right side. Now let's take a look at these two. We can construct a prime implicant using this one and this one like this, using 2 elements. But if you take a look to the left side, we have 2 don't care terms here. So we can take those as well and construct a prime implicant of 4 elements here. Now these 3 are the prime implicants here. Now we need to find out which of these are essential. Essential prime implicants are those which cover at least 1. That is, at least one min term is covered by that prime implicant, which without that prime implicant that won't be covered. So this prime implicant covers these 2 ones, and there is no other prime implicant which covers this. So this is clearly essential. If you look at this one, it is covered by this prime implicant and no other prime implicant is covering this one. So this prime implicant is also essential. If you take a look at this one, it's covering these 2 ones uniquely. There is nothing else covering these 2 ones. So all of these 3 prime implicants are essential here. So the answer is 3.